Hello there and welcome to Science for Sleep, where curiosity gets cozy, science takes its time, and the universe becomes a little gentler before bedtime. Tonight we're looking up at a question that seems simple at first glance, but turns out to be one of the deepest mysteries in astronomy. Why is space so dark when stars are so bright? It sounds almost like a trick question. After all, if you've ever stepped outside on a clear night, you've probably seen hundreds of stars scattered across the sky. If you've been lucky enough to visit a truly dark location, far from city lights, you've likely seen thousands. A pale river of starlight stretching overhead. Tiny points of light filling every direction. And yet, despite all those stars, the sky remains overwhelmingly dark. Most of the universe appears black. Most of what you see when you look upward is not light. It's darkness. That seems a little strange, doesn't it? Imagine walking into a room filled with light bulbs. Not one or two, but billions of them. Imagine the bulbs stretching in every direction farther than you could possibly see. You wouldn't expect that room to be dark. You would expect it to be dazzlingly bright. So why isn't the universe like that? Where does all the light go? And perhaps more importantly, why does darkness seem to win? Before we wander into that mystery, I'd love to ask you something. Where are you listening from tonight? Maybe you're tucked into bed beneath a blanket. Maybe you're sitting in a chair with a cup of tea nearby. Perhaps it's late evening where you are. Perhaps it's already well past midnight. And if you happen to glance at a clock, what time is it right now in your little corner of the world? It's funny, really. Thousands of people may hear these words at completely different moments, some listening under summer skies, others beneath winter clouds, some surrounded by city lights. Others living beneath skies so dark that the Milky Way seems bright enough to cast shadows, yet all of us are looking toward the same universe, the same stars, the same darkness. If you find these sleepy journeys relaxing, interesting, or simply a pleasant way to unwind after a long day, I'd be very grateful if you gave the video a like and perhaps subscribed as well. It helps this quiet little corner of science find fellow travellers who enjoy drifting off with questions about the cosmos. Now then, settle in, get comfortable. There's no rush tonight. The universe has been waiting billions of years for us to ask this question. It can wait a little longer while we get cozy. At first, darkness seems normal. In fact, it seems so normal that most of us rarely question it. When night arrives, we expect darkness. When we enter a room and turn off the lights, we expect darkness. Darkness feels like the default setting. Light feels like the exception. But astronomers learned long ago that intuition can be deceptive. Sometimes the most ordinary things turn out to be the strangest. Consider the ocean. For thousands of years, people looked at the sea and assumed it must simply go on forever. It looked endless. Then exploration revealed coastlines, continents, and boundaries. The truth turned out to be more complicated than appearances suggested. The night sky is similar. It looks ordinary, a black background with bright stars sprinkled across it. Yet hidden inside that ordinary view is a puzzle so profound that it eventually forced scientists to rethink the nature of the universe itself. The mystery begins with a simple observation. Stars are incredibly bright. Not bright in the everyday sense, not bright like a lamp or a flashlight, truly bright. The sun alone produces more energy every second than humanity could consume in millions of years. And the sun is not unusual. Many stars are far brighter. Some produce tens of thousands of times more light, others produce hundreds of thousands. A few extraordinary stars shine with millions of times the sun's luminosity. The universe is filled with these gigantic cosmic furnaces, each one pouring energy into space, each one flooding its surroundings with light, every second, every minute, every year, for millions or even billions of years. That's an astonishing amount of illumination, and there are not merely hundreds of stars, not merely thousands. Our galaxy alone contains hundreds of billions. Current estimates suggest the observable universe contains hundreds of billions of galaxies, each packed with stars. When you multiply those numbers together, you arrive at totals so enormous they become difficult to picture. Trillions, quadrillions, numbers so large they stop feeling like numbers and start feeling like abstract concepts. Yet every one of those stars is producing light. Everyone. So let us perform a little thought experiment. Imagine standing in the middle of an immense forest. Trees surround you in every direction. No matter where you look, eventually your line of sight runs into a tree. Perhaps it's nearby, perhaps it's farther away, but eventually something occupies that space. Now replace every tree with a star. If stars extend endlessly throughout the cosmos, shouldn't the same thing happen? Shouldn't every direction eventually end at the surface of a star? Shouldn't the entire sky glow, not with scattered points of light, not with occasional stars everywhere, continuously bright in every direction? Yet that's not what we see. We see darkness, lots of it. In fact, darkness dominates almost everything. Stars occupy only tiny portions of the sky. The rest appears empty, and that's where our story begins. Astronomers sometimes describe science as the art of taking ordinary observation seriously. A child might ask why the sky is blue. An adult might barely think about it. A scientist takes the question seriously enough to investigate. The same thing happened with the darkness of space. For countless generations, people accepted the night sky exactly as it appeared. Black background, bright stars, end of story. But eventually someone asked a dangerous question. Not dangerous because it threatened anyone. Dangerous because simple questions often expose hidden assumptions. The question was this: should the sky actually be dark? Once you ask that, everything changes, because the answer isn't obvious, and for a long time nobody knew what the answer was. The puzzle became especially important as astronomers learned more about stars. Early civilizations often imagined stars as small lights attached to a celestial sphere, tiny objects decorating the heavens. But telescopes gradually revealed a different reality. Stars were not tiny. They were enormous. The sun itself was a star. The stars visible at night were distant suns. Suddenly the scale of the cosmos expanded dramatically. Every bright point overhead represented something vast, something powerful, something generating unimaginable amounts of energy. That realization made the darkness even stranger. Imagine discovering that every candle in a room is actually a lighthouse. You would immediately wonder why the room remains dim. The universe presents a similar contradiction. The sources of light are unbelievably powerful, yet the overall result seems surprisingly dark. As observations improved, the puzzle only grew. Astronomers found more stars, more galaxies, more evidence that the universe contained staggering quantities of luminous objects. Instead of solving the mystery, every new discovery seemed to deepen it. The cosmos appeared to be overflowing with light. Still, darkness remained king. Tonight, if you were to step outside beneath a clear sky, your eyes would confirm this. You would see stars, perhaps planets. Maybe the faint band of the Milky Way, yet most of the sky would remain black. That blackness feels empty, but appearances can be misleading. In reality, every patch of darkness may contain countless stars too distant for your eyes to detect. Every dark region might hide galaxies beyond imagination. The darkness is not necessarily empty. It's merely dark. And those are not the same thing. That distinction turns out to be important. Very important. Because when astronomers finally began unraveling this mystery, they discovered that darkness wasn't simply the absence of light. It was a clue pointing towards something fundamental about the nature of the universe, something about its history, its structure, its age, even its future. Oddly enough, the darkness above us contains information. The black sky is telling a story. The challenge is learning how to read it. Think for a moment about a campfire. If you're sitting close to it, the fire feels bright and warm, and Move farther away and it becomes dimmer. Keep moving, farther, farther still. Eventually the fire becomes a tiny speck. Then it vanishes entirely. Not because the fire stopped producing light, not because the fire went out, simply because the distance became too great. This seems obvious. But distance changes everything in astronomy. The universe is not merely large, it's staggeringly large. Light itself requires time to cross it. The moon is about 1 second away at light speed. The sun is 8 minutes away. The nearest star beyond the sun is more than 4 years away. Our galaxy stretches across roughly 100,000 light years, and beyond it lie countless other galaxies separated by millions of light years. Space is vast beyond ordinary comprehension, yet even that statement barely captures reality. The distances involved are so enormous that human intuition struggles to keep up, which means the darkness overhead might not be as simple as it first appears. Maybe stars are bright. Maybe there are countless stars. Maybe the universe is flooded with light. And yet perhaps something about distance changes the picture. Perhaps something about the cosmos itself prevents all that starlight from reaching us. Astronomers would spend centuries exploring exactly that possibility. What they eventually discovered transformed our understanding of reality. The answer turned out to involve the age of the universe, the expansion of space, the journey of light across unimaginable distances, and some of the most remarkable ideas ever developed by science. But before any of those answers arrived, there was only the question. A deceptively simple question. A question hiding in plain sight every clear night. Why is space so dark when stars are so bright? The more scientists examined that mystery, the stranger it became. Because if the universe behaved the way many people assumed it did, darkness shouldn't exist at all. The night sky should blaze with light. Every direction should shine. Every patch of darkness should glow. Instead, we find ourselves beneath a vast black canopy scattered with islands of starlight. That contradiction would eventually become one of the most famous puzzles in astronomy. And as more telescopes pointed toward the heavens and more observations accumulated, researchers began realizing that the darkness above us wasn't a trivial detail. It was evidence. Evidence that the universe was not eternal in the way many once imagined. Evidence that light had limits. Evidence that cosmic history mattered. Take a moment and picture a perfectly clear night. No clouds, no moon, no city lights spilling upward from streets and buildings. Just you and the sky. Perhaps you've experienced a night like that before. Maybe during a camping trip far from civilization. Maybe while travelling through a rural area where darkness still rules the landscape once the sun goes down. Under those conditions, the sky can be astonishing. Thousands of stars appear overhead. The Milky Way stretches from horizon to horizon. Constellations become almost difficult to recognise because so many additional stars fill the gaps between them. For many people, it's one of the most beautiful sights on Earth. Yet even beneath the darkest skies available to human eyes, one thing remains true. Most of the sky is still dark. The stars occupy only a tiny fraction of what you're looking at. Darkness fills everything else. Today, that observation feels completely normal. Of course the sky is dark. Night is supposed to be dark. The idea seems so obvious that it hardly feels worth discussing. But astronomers eventually learned that the most dangerous assumptions are often the ones that seem obvious. The moment somebody asks why something is the way it is, ordinary observations can suddenly become extraordinary puzzles. And that's exactly what happened with the darkness of space. For centuries, people simply accepted the night sky as it appeared. There were stars, there was darkness, no mystery, no paradox, nothing to explain. Then astronomy began changing. Telescopes improved. Observations became more precise. Scientists started learning what stars actually were. And that's when the trouble began. Because stars turned out to be far more impressive than anyone had imagined. To ancient observers, stars often appeared as tiny lights attached to the heavens. Beautiful, certainly, Important, absolutely, but small. The invention of the telescope gradually destroyed that picture. Astronomers discovered that stars were not tiny decorations. They were enormous physical objects, gigantic spheres of hot gas, cosmic furnaces powered by processes so energetic that they would have seemed impossible to earlier generations. Then came another realization. The sun itself was a star. That changed everything. The sun dominates our daytime sky. It illuminates entire continents. It drives weather systems. It powers nearly all life on Earth. And yet the sun was merely one star among countless others. The stars visible at night were distant suns. Some were smaller, some were larger, some were vastly more powerful. Suddenly the universe looked very different. Instead of a handful of lights decorating the sky, astronomers found themselves living inside an immense population of stellar objects, each producing tremendous amounts of energy, each radiating light in every direction, every second, every minute, every year, for millions or billions of years. At first, that discovery was exciting. Then it became uncomfortable. Because once scientists understood what stars really were, they began asking a very awkward question. If stars are everywhere, why isn't the sky bright? Notice how simple that question is. No advanced mathematics, no complicated equipment, no exotic physics. Just a straightforward observation, the kind of question a curious child might ask. Sometimes those are the most powerful questions of all. Imagine standing in a dense forest. Trees surround you. Wherever you look, eventually your gaze encounters a trunk, perhaps a nearby trunk, perhaps one farther away. But eventually something blocks your line of sight. Now imagine the forest extending forever. No edges, no boundaries, no end. In that situation, every direction would ultimately contain a tree. You would never be able to look through the forest into empty space because another tree would always be waiting somewhere farther along your line of sight. Astronomers realized something similar might apply to stars. Suppose the universe is infinite. Suppose stars are distributed throughout that infinite universe. Suppose stars have existed forever. Then what happens when you look into the night sky? Every direction should eventually end at the surface of a star. Perhaps a nearby star, perhaps an extremely distant one, but eventually a star. Under those conditions, the sky should not be dark. It should shine continuously. Every patch of darkness should be filled by distant starlight. The entire sky should resemble the surface of the sun, not quite as bright because stars vary in distance and brightness, but bright enough that true darkness would not exist. Yet darkness clearly does exist. You can step outside tonight and verify it yourself. The evidence is visible immediately. Most of the sky remains black. So somewhere in this chain of reasoning something must be wrong. That realization created one of astronomy's most famous puzzles. Today we call it Olbers' paradox, named after the German astronomer and physician Heinrich Wilhelm Olbers. Interestingly, Olbers did not actually invent the idea. Versions of the argument existed long before him. Thinkers had wrestled with it for centuries, but his name eventually became attached to the puzzle, and it remains associated with him today. The paradox itself is remarkably easy to understand. In fact, that's part of what made it so troubling. Complicated problems can often be ignored. Simple problems are harder to escape. The logic seems straightforward. If the universe is infinite, if stars fill that universe, if stars have always existed, then the night sky should be bright. It isn't. Why? For a long time, nobody had a satisfactory answer. That might seem surprising from a modern perspective. After all, we know so much about the cosmos today. But remember, there was a period when scientists possessed only fragments of the larger picture. They knew stars existed. They knew there were many of them. They knew light travelled through space. Yet crucial pieces of information remained missing. Without those missing pieces, the darkness of the night sky looked almost impossible to explain. Naturally, people proposed solutions. Some seemed reasonable at first. One suggestion involved dust. Maybe enormous clouds of dust blocked distant starlight. Perhaps the universe was full of material that absorbed light before it could reach Earth. Problem solved, or so it seemed. Unfortunately, the idea falls apart under closer inspection. Imagine placing a black object in front of a powerful lamp. The object absorbs light, but what happens next? It heats up. Eventually it begins radiating energy of its own. The same principle applies to cosmic dust. If dust absorbed endless amounts of starlight, it would eventually become hot enough to glow. Instead of eliminating the brightness problem, the dust would simply become another source of light. Darkness would still disappear. Astronomers realized that dust alone could not save them. The paradox remained. Another possibility involved the distribution of stars. Maybe stars weren't spread evenly throughout the universe. Maybe there were large empty regions. That idea helped somewhat, but not enough. As long as stars extended infinitely in all directions and had existed forever, the basic problem survived. Eventually every line of sight should encounter starlight. Darkness still had no obvious explanation. This was deeply unsettling. Not because astronomers were afraid of darkness, but because paradoxes often signal that a fundamental assumption is wrong. Science has a long history of discovering hidden mistakes through seemingly simple contradictions. When observations disagree with expectations, one of two things must happen. Either the observations are wrong, or the assumptions are wrong. The night sky kept insisting on darkness. The observations were not the problem. That meant scientists needed to re-examine their assumptions. Maybe the universe wasn't infinite. Maybe stars hadn't existed forever. Maybe space itself behaved differently than expected. Possibilities that once seemed unnecessary suddenly became important. The darkness overhead was forcing astronomers into new territory. In hindsight, this is one of the most fascinating aspects of the story. The puzzle wasn't created by exotic observations from giant telescopes. It wasn't discovered through particle accelerators or spacecraft. It emerged from something everyone could see: the night sky. The same sky observed by farmers, sailors, shepherds, and children throughout human history. The evidence had been visible all along. What changed was the willingness to question it. That willingness sits at the heart of science. Many breakthroughs begin with somebody refusing to accept an ordinary observation at face value. Why is the sky blue? Why do planets move the way they do? Why do objects fall? Why is space dark? Simple questions, enormous consequences. As the 19th century progressed, astronomers accumulated more data. Telescopes revealed greater numbers of stars. Better instruments expanded humanity's view of the cosmos. Instead of solving the paradox, these discoveries often made it worse. More stars meant more light. More light meant a brighter expected sky. Yet the actual sky stubbornly remained dark. Imagine adding thousands of lamps to a room, while the room somehow refuses to become brighter. Eventually you would suspect that something fundamental about the room itself was missing from your understanding. Astronomers reached a similar conclusion. The answer could not simply involve counting stars. Something larger was happening. Something connected to the nature of the universe itself. What made the puzzle particularly frustrating was how intuitive the logic felt. Many scientific mysteries involve complex mathematics. This one did not. Even people with little scientific training could grasp the argument. If stars fill an eternal universe, why isn't everything bright? That simplicity gave the paradox unusual power. It was difficult to dismiss, difficult to ignore, and impossible to fully explain with the knowledge available at the time. The situation became even more intriguing when astronomers started appreciating just how vast the universe might be. Distances between stars were enormous. Distances between groups of stars were even larger, yet no matter how large those distances became, the paradox survived. A very distant star appears dimmer. That's true, but there are also more stars at greater distances. The two effects balance in a surprising way. Each shell of space contributes additional light. Keep adding shells forever and the total brightness keeps growing. Again and again, the calculations seem to point toward a bright sky. Reality refused to cooperate. The darkness overhead remained undefeated. At this stage, astronomers were standing on the edge of a major discovery without fully realizing it. The paradox was not merely about stars. It was not merely about darkness. It was secretly about the history of the universe. The answer depended on something nobody yet understood, something that would eventually transform astronomy forever, because hidden inside the puzzle was an assumption so common that almost everyone accepted it automatically. The assumption was that the universe had always existed. No beginning, no starting point, no cosmic dawn, an eternal cosmos stretching infinitely into the past. That idea seemed reasonable for a very long time. Many scientists found it appealing. After all, if the universe exists now, perhaps it simply always existed. Why assume otherwise? The paradox slowly revealed the weakness in that assumption. The darkness of the night sky was trying to tell astronomers something. The message was subtle, easy to miss, but incredibly important. Maybe stars had not been shining forever. Maybe the universe itself had a history. Maybe there was a time before galaxies formed. Maybe there was a moment when the first stars ignited. If that were true, distant light might not have had enough time to reach us. Suddenly the darkness becomes less mysterious. Not because there isn't enough light, but because not all of that light has arrived yet. That idea would eventually lead astronomers toward one of the greatest discoveries in scientific history. The realization that the universe has an age, a beginning, a measurable history stretching backward through time. Yet before that solution emerged, generations of scientists wrestled with the paradox. They debated it, calculated it, proposed explanations, rejected explanations, returned to it again. The darkness above them remained unchanged, patient, silent, waiting. And the remarkable thing is that the night sky still presents exactly the same challenge today. You can step outside and look upward. You'll see the same darkness that puzzled astronomers centuries ago. The same black background, the same scattered stars, the same apparent contradiction. The difference is that we now possess clues those earlier thinkers lacked. Clues hidden in the age of the cosmos itself. Picture yourself standing beneath the darkest sky you can imagine. No streetlights, no passing cars, no glowing windows in the distance. Just darkness overhead and a sea of stars stretching across the heavens. Now imagine that every star you can see is merely one grain of sand on an enormous beach, because that's much closer to reality. The stars visible to your eyes represent only a tiny fraction of what actually exists. Beyond them are countless fainter stars. Beyond those are entire galaxies. Beyond those are more galaxies still. The deeper astronomers looked into space, the more crowded the universe appeared. At first glance, that sounds perfectly reasonable. Of course there are many stars. Of course there are many galaxies. The universe is large. But eventually scientists realized that this abundance created a serious problem, not a small problem. Not a technical inconvenience, a genuine contradiction, a contradiction hidden in plain sight every single night. The puzzle became known as Olber's paradox, and despite its intimidating name, the basic idea is remarkably simple. In fact, it is so simple that once you hear it, it becomes difficult not to think about it whenever you look at the stars. Let's begin with a thought experiment. Imagine an enormous forest. The forest extends in every direction: north, south, east, west, far beyond anything you could ever explore. There are trees everywhere. Now stand in the middle and look outward. Eventually your line of sight will encounter a tree, maybe nearby, maybe far away, but eventually a tree. Now imagine the forest extending forever. No edge, no beginning, no end. Under those conditions, every direction would ultimately contain a tree. You would never find an empty line of sight. Something would always be there. Astronomers realized that the same logic should apply to stars. Suppose the universe extends infinitely in all directions. Suppose stars are distributed throughout that infinite universe. Then every line of sight should eventually end at a star. Not necessarily a nearby one, not necessarily a bright one, but eventually a star. And if every line of sight ends at a star, the entire sky should glow. Darkness should disappear. Yet darkness obviously exists. The night sky remains overwhelmingly black. That was the paradox. At first, many people underestimate how serious this problem actually is. They instinctively think, well, distant stars are dim. That's true. A distant star does appear fainter than a nearby one. But here's the clever part. As distance increases, the number of stars also increases. A lot. Imagine drawing an invisible sphere around yourself. Now imagine a larger sphere, then an even larger sphere. Each larger sphere contains vastly more volume than the previous one. More volume means more stars, many more. The farther you look into space, the more stars become available to contribute light. The mathematics produces an interesting result. Individual stars grow dimmer with distance, but the number of stars grows at just the right rate to compensate. Each layer of space contributes roughly the same amount of brightness. Layer after layer, shell after shell, endlessly. Add enough shells together and the sky should become brilliant. That's what troubled astronomers. The numbers seemed straightforward. The logic seemed unavoidable. Yet the conclusion was completely wrong. Reality refused to cooperate. The sky remained dark. Imagine entering a room filled with candles. One candle illuminates a small area. 10 candles create more light. 1,000 candles create far more. Now imagine billions upon billions of candles extending endlessly in every direction. At some point, the room would become overwhelmingly bright. The darkness would vanish. Stars behave similarly. Every star contributes light. Perhaps only a tiny amount. But when enough stars exist, those tiny contributions add up. Olber's paradox essentially asks a very uncomfortable question. Why don't they add up? Why doesn't the sky shine? This question became especially important during the 18th and 19th centuries. At that time, many scientists viewed the universe as eternal. The idea seemed natural. The cosmos existed now. Perhaps it had always existed. Perhaps it would always exist. An eternal universe felt stable and sensible. But Olber's paradox exposed a weakness in that picture. An eternal universe filled with stars should produce a bright sky. Since the sky is dark, something must be wrong. Either the universe isn't eternal, or it isn't infinite, or stars aren't distributed the way people imagined, or some completely different explanation exists. Whatever the answer might be, the paradox demanded one. The universe was sending contradictory messages. One message said there are countless stars. The other said darkness dominates the sky. Astronomers needed a way to reconcile both observations. Naturally, proposed solutions appeared. One of the earliest ideas involved cosmic dust. Perhaps enormous clouds of dust blocked distant starlight before it could reach Earth. On the surface, that sounds reasonable. After all, dust can block light. We experience that effect constantly. Fog reduces visibility. Smoke dims distant lights. Dusty air can obscure objects. Why couldn't cosmic dust do the same thing? The problem is that dust cannot simply absorb energy forever. Eventually it heats up, and when something heats up, it radiates energy. Imagine placing a dark object in front of a powerful heater. The object absorbs energy. Its temperature rises. Soon it begins giving off energy itself. The same principle applies in space. If dust absorbed endless amounts of starlight, it would eventually become hot enough to glow. Instead of solving the brightness problem, the dust would become another source of brightness. Darkness would still lose. Astronomers realized dust alone could not rescue the eternal universe. The paradox survived. Other explanations encountered similar difficulties. Again and again, scientists found themselves returning to the same uncomfortable conclusion. The darkness overhead was trying to tell them something important. The challenge was figuring out what. One reason Olbers' paradox fascinated astronomers is that it transformed darkness into evidence. Most people think of darkness as the absence of information. Astronomers learned the opposite. The darkness itself contained information. In fact, it contained some of the most valuable information imaginable. Think about that for a moment. Every dark patch of sky is evidence. Evidence about the nature of the universe. Evidence about cosmic history. Evidence about the limits of light. Evidence about time itself. The blackness above your head is not merely empty space. It is a clue. A gigantic clue stretching across the entire sky. As telescopes improved, the paradox became even more intriguing. Early astronomers could only see a few thousand stars. Later instruments revealed millions, then billions, then galaxies beyond galaxies. Every technological advance uncovered more sources of light. Instead of making the universe simpler, the discoveries intensified the mystery. The cosmos seemed increasingly crowded, yet the darkness remained. Imagine discovering more and more lamps inside a building, while the hallways somehow refused to become brighter. Eventually you would suspect that your understanding of the building itself was incomplete. Astronomers reached a similar conclusion regarding the universe. The problem could not be solved merely by counting stars. Something deeper was happening, something connected to the structure of reality. The paradox became one of those rare scientific problems that sit quietly in the background for generations. Everyone knows about it. Everyone recognizes its importance, yet the answer remains elusive. Some of history's greatest scientific questions behaved exactly this way. The motion of planets before Newton, the nature of heat before thermodynamics, the origin of species before Darwin. Olbers' paradox belonged to that category. A deceptively simple question hiding profound implications. What made the paradox especially powerful was that it required no sophisticated equipment to appreciate. Anyone could understand it. Look upward, observe darkness, consider the number of stars, notice the contradiction. The puzzle practically explains itself. In many ways, it represents science at its most elegant, a straightforward observation leading toward a revolutionary conclusion. Eventually, astronomers began questioning assumptions they had previously accepted without much scrutiny. Maybe the universe wasn't eternal, maybe stars had not existed forever. Maybe cosmic history mattered. Those ideas seem obvious today. At the time, they were much less obvious. Remember, there was once no accepted Big Bang theory, no established age for the universe, no evidence that galaxies were moving apart. Many concepts familiar to modern readers had not yet been discovered. Scientists were working with an incomplete picture. Olbers' paradox was one of the clues revealing those missing pieces. Like a detective investigating a crime scene, astronomy was beginning to notice inconsistencies. The evidence didn't fit the prevailing story. Something fundamental had been overlooked. And often in science, the most important breakthroughs occur when somebody finally asks whether the assumptions themselves might be wrong. The paradox slowly pushed researchers toward exactly that realization. Perhaps the universe had a beginning. Perhaps stars switched on at some point in cosmic history. Perhaps there was a time when starlight simply didn't exist. That possibility changes everything, because if stars have not been shining forever, then some of their light may still be travelling toward us. The universe suddenly acquires a history, a timeline, a finite age. Darkness becomes understandable, not because there isn't enough light, but because the cosmos hasn't had infinite time to fill every direction with starlight. Yet astronomers weren't quite ready to reach that conclusion. More discoveries still lay ahead, more observations, more evidence. The solution would emerge gradually rather than all at once. What makes this story so satisfying is that the final answer eventually explained far more than the darkness of the night sky. It helped reveal the age of the universe, the evolution of galaxies, the journey of light across immense distances, even the expansion of space itself. A simple question about darkness opened the door to some of the largest ideas in modern cosmology. That often happens in science. A modest question leads unexpectedly toward enormous answers. Why is the sky blue? Why do apples fall? Why is space dark? The question appears small, the consequences become vast, and Olbers's paradox remains one of the finest examples of that pattern. It begins with an ordinary observation available to anyone willing to look upward after sunset. Then it quietly dismantles assumptions about infinity, eternity, and the cosmos itself. The paradox forces us to recognize that the universe cannot simply be an unchanging stage that has existed forever. Imagine receiving a letter from a friend. You check the mailbox. You open the envelope. You read the message. Simple enough. But now imagine that friend lives very far away, not in another city, not in another country. Suppose they live on the other side of an ocean during a time before airplanes, radio, or the internet. The letter might take weeks to arrive, perhaps months. When you finally read it, you're not experiencing the present moment of the person who wrote it. You're seeing the past. The message was written long ago. The information has simply taken time to reach you. Light behaves in exactly the same way. That realization turns out to be one of the most important discoveries in astronomy. And surprisingly, it provides the first major clue to solving the mystery of the dark night sky. For most of human history, people assumed light travelled instantly. The idea seemed reasonable. Turn on a lamp and the room brightens immediately. Light appears so fast that everyday experience offers no hint of any delay. But nature often hides its most interesting secrets behind scales too large for ordinary life. In the 17th century, astronomers began uncovering evidence that light possesses a finite speed. Not infinite, not instantaneous, fast beyond imagination certainly, but still limited. Today we know that light travels at roughly 300,000 kilometers per second. That is extraordinarily fast. Light could circle Earth more than 7 times in a single second. It could travel from New York to Tokyo in less than a blink. Yet even that astonishing speed encounters difficulties when confronted with the immense size of the universe. Space is simply too large. The distances are too great. Even light requires time to cross them. The moon appears close in the sky, yet moonlight takes about 1.3 seconds to reach Earth. When you look at the moon, you're seeing it as it existed slightly more than a second ago. The sun appears nearby compared to the stars. Even so, sunlight requires approximately 8 minutes to arrive. If the sun somehow vanished this instant, Earth would continue receiving sunlight for another 8 minutes before darkness arrived. Already the universe is revealing something strange. Looking outward means looking backward. Distance creates delay. The farther away something is, the older the information becomes. That principle grows increasingly dramatic as distances increase. The nearest star beyond the Sun is Proxima Centauri. Its light takes more than 4 years to reach us. When astronomers observe Proxima Centauri tonight, they see a version of the star that existed more than 4 years ago. Not the star as it is now, the star as it was. 4 years may not sound especially impressive, but astronomy quickly leaves ordinary scales behind. Some stars visible to the naked eye are hundreds of light years away, others are thousands. Many objects observed through powerful telescopes lie millions or billions of light years from Earth. Every observation becomes a glimpse into history. The night sky is not a collection of objects existing in the present. It is a collection of messages arriving from different moments in the past. A nearby star might be delivering information a few years old. A distant galaxy might be delivering information millions of years old. The most remote objects visible to modern telescopes are showing us events that occurred billions of years ago. Astronomy is often described as a form of time travel, not because we physically move through time, but because light carries history across the cosmos. Every telescope functions as a machine for observing the past. Once scientists fully appreciated this fact, Olbers' paradox began looking very different. Remember the paradox. If stars fill an infinite universe and have existed forever, the sky should glow brightly in every direction. That argument assumes something important. It assumes that starlight has had enough time to reach us. But what if that assumption is wrong? What if some stars are so distant that their light simply hasn't arrived yet? Suddenly the puzzle changes. Imagine standing in the middle of an enormous forest at night. Somebody begins lighting campfires throughout the forest. Nearby fires become visible immediately. More distant fires take longer to notice. The farthest fires remain unseen for quite some time, not because they aren't burning, not because they aren't producing light, but because their light hasn't reached your eyes yet. The universe may operate similarly. If the cosmos has a finite age, then there has only been a limited amount of time available for light to travel. That limitation creates a boundary. Astronomers sometimes call it a cosmic horizon. Beyond that horizon lie regions whose light has not yet had enough time to reach Earth. Those regions may exist. They may contain stars, they may contain galaxies, they may contain unimaginable amounts of light. But if their light hasn't arrived, they remain invisible. An invisible light cannot brighten our sky. This realization represents one of the major breakthroughs in understanding the darkness of space. The night sky is dark partly because the universe has not existed forever. There hasn't been enough time for every possible beam of starlight to reach us. That might seem obvious now. For earlier generations of astronomers, it was revolutionary, because it implied something profound. The universe has a history, a beginning, a measurable age. The cosmos is not infinitely old. It has not been producing starlight forever. At some point, stars first appeared. Before that, no starlight existed at all. To appreciate the significance of this idea, consider another thought experiment. Imagine entering a vast cave. The cave is completely dark. Someone standing beside you turns on a flashlight. Light begins spreading outward. If the cave were infinitely large, enormous regions would remain dark for quite some time, not because the flashlight is weak. Not because darkness is somehow fighting back, simply because light requires time to travel. The expanding sphere of illumination cannot appear everywhere instantly. The same principle applies on cosmic scales. Stars are powerful, incredibly powerful, but they are not infinitely old. Their light is still propagating through the universe. Some of it has reached us, much of it has not. As scientists explored these ideas, evidence began accumulating that the universe itself has a finite age. Observations suggested a cosmos that changes over time. Stars are born, stars age, stars die, galaxies evolve. Everything appears dynamic rather than eternal. Then came one of the greatest discoveries in scientific history, the realization that the universe is expanding. That story belongs largely to later parts of our journey, but its implications began transforming astronomy almost immediately. If the universe is expanding today, then looking backward implies a denser past. Continue tracing that history far enough, and the cosmos approaches an early state vastly different from what we see now. A beginning emerges, not necessarily a beginning in the philosophical sense, but certainly a beginning to the observable history of the universe. Modern measurements indicate that the universe is approximately 13.8 billion years old. That number is difficult to comprehend. It sounds enormous because it is enormous. 13.8 billion years is longer than the existence of Earth, longer than the existence of the Sun's planetary system, longer than multicellular life, longer than almost everything we can imagine. Yet despite its immense size, the number remains finite. The universe has not existed forever, and finite age means finite travel time. Finite travel time means some light remains en route. That changes everything. Suppose a galaxy lies 20 billion light-years away. Even if it shines brilliantly, its light cannot reach us if the universe itself is only 13.8 billion years old. The message has not had enough time to arrive. The photons are still travelling. The darkness remains. This concept is surprisingly powerful. The black regions of the night sky are not necessarily empty. Many may contain objects whose light has not yet reached Earth. The darkness does not automatically indicate absence. Sometimes it indicates delay. The distinction matters enormously. Imagine standing on a beach watching ships approach from beyond the horizon. Before a ship becomes visible, it still exists. It is still moving. It is still crossing the ocean. You simply haven't received visual confirmation yet. Astronomy operates on similar principles. Much of the universe lies beyond what light has had time to reveal. That limitation turns darkness into a natural consequence of cosmic history. There is another fascinating aspect to this story. Every improvement in telescope technology allows us to see farther, and seeing farther means looking deeper into the past. Astronomers routinely observe galaxies whose light began travelling long before Earth existed in its present form. Some of the most distant galaxies ever detected are observed as they appeared when the universe was only a small fraction of its current age. Think about how remarkable that is. A telescope positioned on Earth can collect photons that departed their source billions of years ago. Those photons have been crossing space for longer than complex animals have existed, longer than dinosaurs walked the planet, longer than continents occupied their current positions. Then, after an unimaginable journey, they arrive inside a scientific instrument. The information finally reaches us. The cosmic letter is delivered, and because of that finite travel time, the darkness of space begins making sense. Not complete sense yet. Additional pieces remain missing. But a major part of the puzzle has fallen into place. The universe is not infinitely old. Light travels at a finite speed. Some light simply hasn't arrived. Darkness is therefore expected. The solution sounds almost obvious once stated. Many profound scientific discoveries share that quality. They appear simple afterward. The challenge lies in reaching them. For centuries, astronomers lacked enough information to connect all the pieces. The paradox lingered. The sky remained dark. The explanation remained hidden. Eventually, observations revealed the truth. The darkness overhead was telling us something fundamental about cosmic history. The night sky contains evidence that the universe had a beginning, evidence that light requires time to travel, evidence that we occupy a specific moment in an evolving cosmos. Yet even this explanation does not fully solve the mystery. Because another factor is quietly at work, a factor even stranger than finite age. Suppose every photon eventually reaches us. Suppose enough time passes. Would the sky eventually become bright? At first glance, perhaps. Imagine standing on a long railway platform. A train begins moving away from you. At first, you can hear every detail clearly. The rumble of the wheels, the hum of the engine, the occasional metallic clank from somewhere deep inside the carriages. As the train gets farther away, those sounds become weaker. The details begin to fade. Eventually, the train becomes a distant shape on the horizon. You know it's still there. You know it's still moving. But the information reaching you has changed. Distance has altered your experience of it. The universe does something similar with light, though the reality is far stranger than a train disappearing into the distance. By the early 20th century, astronomers had already made enormous progress towards solving the mystery of the dark night sky. They had learned that light travels at a finite speed. They had begun realizing that the universe has a finite age. Those discoveries explained part of the puzzle. Some starlight simply hasn't had enough time to reach us. Yet another question remained. Was that enough? Could the finite age of the universe completely explain why the sky remains dark? The answer turned out to be no. There was another factor at work, a factor nobody had anticipated for most of human history. Space itself is expanding. That statement sounds simple. It sounds almost innocent. But hidden inside those 4 words is one of the most astonishing discoveries ever made. Because when people first hear that the universe is expanding, they often imagine galaxies moving through space, the way airplanes move through the sky. That's not quite right. The reality is stranger. The galaxies are not simply moving through space. Space itself is stretching. To understand why that matters, let's begin with an analogy. Imagine drawing several dots on the surface of a balloon. Now start inflating the balloon. As the rubber expands, every dot moves farther away from every other dot. Notice something important. The dots themselves are not crawling across the surface. The surface itself is stretching. The increasing distance comes from the expansion of the balloon. Astronomers often use this example because it captures the basic idea surprisingly well. The universe behaves in a somewhat similar fashion. On the larger scales, space is expanding. Galaxies become more separated over time because the fabric of the cosmos itself grows. The discovery arrived gradually. For centuries, many scientists assumed the universe was static, stable, unchanging on the larger scales. That assumption felt reasonable. After all, the stars did not appear to be rushing away from one another. The cosmos looked permanent. Then observations started telling a different story. During the 1920s, astronomers made a remarkable discovery. Galaxies appeared to be moving away from us. Not just a few galaxies, most galaxies. The farther away a galaxy was, the faster it appeared to be receding. At first, this result seemed almost unbelievable. Imagine walking into a room and discovering that every wall is moving away from you simultaneously. Your first reaction might be to suspect a mistake. But the evidence continued accumulating. Again and again, observations pointed toward the same conclusion. The universe was expanding. One of the key figures in this discovery was the American astronomer Edwin Hubble. By studying distant galaxies, he found a relationship that transformed cosmology forever. More distant galaxies showed greater recession. The pattern was clear. Space was not static. It was changing. Once astronomers accepted this reality, an important consequence immediately emerged. If space expands, then light travelling through that space must also be affected. This is where our story reconnects with the darkness of the night sky. Imagine drawing a wave on a rubber band. Now stretch the rubber band. The wave stretches too. Its peaks become farther apart. Its wavelength increases. Something similar happens to light crossing an expanding universe. Light travels as an electromagnetic wave. As space stretches, the wavelength of that light stretches along with it. Astronomers call this phenomenon redshift. The name comes from the visible spectrum. Red light possesses longer wavelengths than blue light. When light stretches, it shifts toward the red end of the spectrum. Continue stretching enough, and the light eventually moves beyond visible red entirely. It enters infrared wavelengths. Stretch it further still, and it becomes microwave radiation. Further again, and it becomes radio waves. The light has not disappeared. The energy still exists, but it no longer appears visible to human eyes. This realization proved revolutionary. Suddenly, astronomers understood that some of the universe's light might still be reaching us while remaining invisible. The darkness overhead did not necessarily mean an absence of photons. It could mean that many photons had been stretched beyond visibility. Imagine taking a bright blue painting and gradually shifting every colour toward longer wavelengths. Eventually, the image would become unrecognizable to human vision. The information remains present, Your eyes simply cannot detect it. The expanding universe performs a similar transformation on ancient light. Consider a photon beginning its journey billions of years ago. It departs from a distant galaxy as visible light, perhaps yellow, perhaps blue, perhaps white. Then the photon spends billions of years crossing expanding space. Throughout that journey, the universe continues growing. The wavelength stretches, the energy decreases. By the time the photon finally arrives, it may no longer belong to the visible spectrum at all. To human eyes, it contributes nothing to the brightness of the night sky. The photon arrives, the darkness remains. This effect becomes increasingly important for extremely distant objects. Nearby stars experience very little cosmological stretching. Their light reaches us before expansion significantly alters it. But galaxies billions of light years away tell a different story. Their photons have travelled enormous distances for enormous periods of time. Expansion has had plenty of opportunity to do its work. Many arrive heavily redshifted. Some arrive stretched far beyond visible wavelengths. This means the universe is continuously hiding part of its own light from us. Not intentionally, of course, merely as a consequence of expansion. The cosmos produces enormous quantities of radiation. Much of that radiation never reaches our eyes in its original form. Instead, it arrives transformed, invisible. One way to appreciate this effect is to imagine a cosmic accountant keeping track of energy. Suppose a distant galaxy emits 1 trillion units of visible light. By the time those photons cross billions of years of expanding space, their wavelengths have stretched dramatically. The energy per photon decreases, the original brilliance fades, the galaxy appears dimmer than it otherwise would. Multiply this process across billions of galaxies, and the impact becomes enormous. The night sky grows darker, not because the light vanished, because the universe diluted it. This idea would have sounded almost magical to earlier generations. Space itself influencing light, space itself expanding. These concepts were far removed from ordinary experience, yet modern observations confirm them repeatedly. Every major telescope reveals evidence of cosmic expansion. Every survey of distant galaxies reinforces the picture. The universe is not static, it evolves, it grows. And that growth changes the appearance of everything within it. There is a certain irony here. The darkness of space is partly caused by the universe becoming larger. As the cosmos expands, ancient starlight becomes increasingly stretched. The process acts like a gigantic cosmic dimmer switch operating over billions of years. Brightness slowly fades. Visible light drifts into invisibility. Darkness gains ground. Imagine listening to music played from a speaker mounted on an expanding rubber sheet. As the sheet stretches, the sound waves stretch too. The pitch gradually drops lower and lower. Eventually the frequencies fall below human hearing. The music still exists. You simply cannot hear it anymore. Redshift performs an analogous trick with light. The universe stretches the wavelengths until many move beyond human vision. The photons continue arriving. Our eyes remain unaware of them. One of the most extraordinary examples involves the oldest light we can observe. Today, astronomers detect a faint microwave glow filling the entire cosmos. This radiation originally emerged as brilliant light billions of years ago. At the time, the young universe glowed intensely. If human eyes had existed then, they would have seen a radiant cosmic fog. Over billions of years, expansion stretched that light dramatically. Visible wavelengths became microwaves. Brightness became subtle background radiation. The ancient glow still surrounds us. Yet our eyes perceive only darkness. The lesson is profound. Darkness is not necessarily empty. Darkness is not necessarily lightless. Darkness may simply contain light that has changed form. As astronomers continued studying cosmic expansion, They realized the solution to Olber's paradox involved multiple factors working together. The finite age of the universe limits how much light can reach us. The finite speed of light prevents us from seeing beyond a certain horizon. And cosmic expansion continuously stretches and weakens the light that does arrive. Together, these effects transform what would otherwise be an overwhelmingly bright cosmos into the dark universe we observe. The night sky begins making more sense, not because stars are weak, not because galaxies are rare, not because the cosmos lacks illumination. The opposite is true. The universe contains astonishing amounts of light, but age, distance, and expansion conspire to hide much of it from view. Every dark region overhead carries evidence of these processes. Every black patch of sky reflects billions of years of cosmic history. The darkness is not merely the absence of brightness, it is the visible signature of an evolving universe. Some of the most important discoveries in astronomy began with scientists noticing that something looked slightly wrong, not dramatically wrong, not the kind of wrong that immediately overturns entire fields of study, just a small inconsistency. A detail that refused to fit, a tiny clue that became impossible to ignore. The story of redshift starts exactly that way. Astronomers had spent centuries studying the stars. They measured their positions, tracked their movements, and analysed their light. By the early 20th century, telescopes had become powerful enough to reveal objects far beyond our own galaxy. What once appeared as faint cloudy smudges were gradually recognised as enormous collections of stars, entire galaxies, island universes scattered throughout the cosmos. At first, these discoveries seemed to raise as many questions as they answered. How far away were these galaxies? How large was the universe? Had it always existed this way? Nobody knew. Then scientists began examining the light arriving from those distant galaxies, and the light seemed to be carrying a message, a strange message, a message hidden inside colour. To understand what they found, let's start with something familiar. Imagine hearing an ambulance drive past. As it approaches, the siren sounds slightly higher in pitch. Once it passes and moves away, the pitch drops lower. You've probably heard this effect countless times. The sound itself isn't changing at the source. The siren continues producing the same note. What changes is the motion between you and the ambulance. As the vehicle approaches, sound waves become compressed. As it moves away, the waves become stretched. Physicists call this the Doppler effect. It's one of those scientific ideas that sounds complicated until you realize you've experienced it your entire life. Light can behave similarly. Although light isn't a sound wave, it possesses wavelengths. Blue light has relatively short wavelengths. Red light has longer wavelengths. If those wavelengths become stretched, the light shifts toward the red end of the spectrum, hence the name redshift. When astronomers first began measuring the light from distant galaxies, they discovered something extraordinary. Most galaxies appeared redshifted. Their light looked stretched. Again and again. Galaxy after galaxy. Direction after direction. The same pattern emerged. The universe seemed filled with objects whose light had been pulled toward longer wavelengths. At first, this observation was puzzling. Then it became revolutionary. Because stretched light suggested increasing distance. The galaxies were moving away, not just a few, most of them. And the farther away they were, the more stretched their light appeared. The farther away a galaxy sat, the greater its redshift. It was one of the most important clues in the history of science. Space wasn't static. The cosmos wasn't standing still. The universe was expanding. Today that idea feels familiar because we've grown up hearing it. But try placing yourself in the shoes of an astronomer a century ago. For generations, many scientists assumed the universe was eternal and largely unchanging. The stars seemed fixed. The heavens seemed permanent. Then suddenly the evidence began pointing somewhere entirely different. The universe had a history. The universe evolved. The universe changed. and the proof was arriving in the form of faint stretched light crossing unimaginable distances. That realization alone was remarkable. Yet for our story tonight, another consequence matters even more. Redshift doesn't merely tell us that galaxies are receding, it also tells us why the universe appears darker than we might expect. Remember the puzzle we've been following. Stars are bright. Galaxies contain billions of stars. The observable universe contains hundreds of billions of galaxies. So why isn't the sky flooded with light? The finite age of the universe gave us part of the answer. Some light simply hasn't had enough time to arrive. But redshift introduces another factor. The light that does arrive is not necessarily arriving unchanged. The universe stretches it, and that stretching matters enormously. Think of a loaf of bread baking in the oven. Before it rises, you might place raisins throughout the dough. As the bread expands, the raisins move farther apart. The raisins themselves aren't growing much. The dough between them is stretching. Now imagine that instead of raisins, you have tiny light waves embedded in the dough. As the dough expands, the waves stretch too. Their wavelengths become longer. Their energy becomes lower. That is essentially what happens to light travelling across the expanding cosmos. The photon begins its journey one way. It arrives another. A beam of visible light leaving a galaxy billions of years ago may no longer be visible when it reaches us. The universe stretches it along the way. The effect becomes increasingly dramatic with distance. Nearby stars experience very little redshift. Their light doesn't travel long enough for cosmic expansion to significantly alter it. The sun's light reaches Earth in 8 minutes. The nearest stars require only a few years. Not much stretching occurs, but distant galaxies tell a different story. Some photons have spent billions of years crossing the universe. During that time, the cosmos continues expanding. The stretching accumulates. The wavelengths grow longer and longer. The energy gradually fades. Eventually, visible light can be transformed into infrared radiation. Stretch it further and it becomes microwave radiation. Further still, and it becomes radio waves. The original light hasn't disappeared. It still exists, but it has moved beyond the range detectable by human eyes. This is one of the most important ideas to grasp when thinking about cosmic darkness. Darkness does not necessarily mean a lack of light. Sometimes darkness means the light has changed form. Imagine possessing eyes that could detect radio waves. The universe would look completely different. Regions that appear dark to us might glow. Invisible structures would become visible. Entire portions of reality currently hidden from human vision would suddenly emerge. Our experience of darkness depends heavily on the limitations of our senses. Human eyes are remarkable instruments, but they detect only a tiny slice of the electromagnetic spectrum. Visible light occupies a narrow range between longer and shorter wavelengths. Beyond that range lies an enormous territory of radiation, infrared, microwaves, radio waves, ultraviolet, X-rays, gamma rays. The universe produces all of them, yet our eyes remain blind to most of the show. Redshift pushes ancient starlight into those invisible territories, and as more and more photons leave the visible spectrum, the night sky grows darker. The process is subtle. Individual photons do not suddenly vanish. Instead, they slowly lose energy as their wavelengths stretch. Picture a spring. Pull gently and it lengthens slightly. Pull further and it becomes increasingly extended. The same basic principle applies to light waves moving through expanding space. Longer wavelength means lower energy. Lower energy means reduced brightness. Over billions of years, the effect becomes profound. Astronomers sometimes describe the universe as a place where ancient light grows tired, not because photons literally become exhausted. Photons don't experience fatigue, but the image captures something important. The oldest light arriving today has travelled extraordinary distances. The expanding cosmos has stretched it continuously throughout its journey. By the time it reaches us, much of its original energy has faded. That fading contributes directly to the darkness above us. There is something strangely beautiful about this idea. When you look into a dark patch of sky, you may not actually be looking at emptiness. You may be looking through oceans of ancient redshifted light. Photons that once blazed brightly, photons that have spent billions of years crossing the universe, photons transformed by expansion until they slipped beyond human vision. The darkness becomes less empty and more mysterious. It hides things rather than lacking them. In fact, some of the oldest light in existence provides a perfect example. Long before stars existed, the young universe glowed intensely. The early cosmos was filled with radiation. If human eyes could somehow travel back far enough, they would not encounter darkness. They would encounter brightness, immense brightness. The entire universe glowed. But that ancient light has spent billions of years travelling through expanding space. The wavelengths stretched, again and again, year after year, billion after billion. Today, that same radiation survives as microwaves, invisible microwaves. The glow remains, the brightness remains, yet our eyes perceive darkness. Scientists eventually discovered this ancient radiation and named it the cosmic microwave background. We'll spend more time with it later. For now, what's important is what it reveals about darkness itself. The universe can appear dark while still containing enormous quantities of light. Visibility and existence are not the same thing. Human eyes measure only a small fraction of reality. The cosmos extends far beyond those limits. As astronomers built better instruments, they began detecting increasingly redshifted objects. Some galaxies appeared so distant that their light had been stretched dramatically before arrival. What started as visible light arrived as infrared radiation. Without specialized telescopes, those galaxies would remain hidden, invisible, absent from the night sky despite their enormous brightness. This realization transformed observational astronomy. Scientists could no longer rely solely on visible light. To understand the universe fully, they needed instruments capable of detecting radiation beyond human vision. Infrared telescopes became essential. Radio telescopes became essential. Observatories capable of capturing every portion of the electromagnetic spectrum became crucial. Each new wavelength revealed previously hidden parts of the cosmos, and almost every discovery reinforced the same lesson. The universe contains far more light than the night sky suggests. Redshift hides much of it. Expansion transforms much of it. Distance weakens much of it. Yet it remains there, crossing space, carrying information, telling stories about ancient galaxies and vanished eras. There's another consequence worth considering. Because redshift becomes stronger with distance, looking farther into space means looking deeper into cosmic history. The most distant galaxies we observe are not merely far away, they are young. Or more precisely, we see them when the universe was young. Their light began travelling toward us billions of years ago. The farther we look, the closer we approach the universe's early history, and the more stretching that light has experienced. Distance and time become intertwined. Ancient light arrives altered. History arrives redshifted. The universe effectively ages the light during its journey. By now, the solution to the darkness puzzle is becoming clearer. Stars are bright. Galaxies are bright. The cosmos contains staggering amounts of illumination, but several effects work together. The universe has a finite age. Light travels at a finite speed. Space expands. Ancient photons become stretched. Visible radiation drifts into invisible wavelengths. Brightness fades. Darkness survives. Yet one important question remains. If redshift hides so much light from view, where exactly does all that ancient stretched radiation go? What happens to the oldest light in existence? And how did astronomers finally detect it? Walk into a room at night and switch off the lights. For a moment, everything seems dark. Your eyes adjust slowly. Shapes begin emerging from the shadows. A chair becomes visible. A bookshelf appears. Perhaps a faint glow slips through a window from a distant street lamp. Yet even after your vision adjusts, you remain unaware of most of the light around you. Radio waves pass through the room. Infrared radiation streams from warm objects. Signals from satellites move silently through the walls. Wireless networks fill the air. None of it is visible. None of it enters your conscious experience, and yet it is there. The room is not truly dark. It is merely dark to human eyes. That distinction turns out to be incredibly important. In fact, it may be one of the most important ideas in all of astronomy. Because when people look into space, they often assume darkness means emptiness. Darkness suggests absence, a lack of activity, a lack of energy, a lack of light. The universe repeatedly teaches us otherwise. The cosmos is overflowing with radiation, overflowing with information, overflowing with light. Much of it simply lies beyond the narrow limits of human vision. Tonight, if you step outside and look upward, your eyes will reveal a familiar picture. Stars scattered across a black background. Perhaps a planet or two. Perhaps the pale band of the Milky Way stretching overhead. The view feels complete. It feels like you're seeing the universe, but in reality, you're seeing only a tiny fraction of what exists. Imagine listening to an orchestra while wearing earplugs that allow you to hear only a few instruments. You might hear the violins, you might hear a flute. Everything else would vanish. The music would seem sparse and incomplete. Not because the orchestra lacks sound, because your ears lack access. Human vision operates similarly. Our eyes detect only a narrow slice of the electromagnetic spectrum. Visible light occupies a surprisingly small range of wavelengths. Shorter wavelengths appear blue and violet. Longer wavelengths appear orange and red. Everything we normally call light exists within that tiny interval. Yet beyond it lies an enormous invisible landscape. Ultraviolet radiation, infrared radiation, microwaves, radio waves, X-rays, gamma rays. The universe produces all of them, in astonishing quantities. Most pass completely unnoticed by our eyes. This fact remained hidden for much of human history. People naturally assumed vision revealed reality. After all, sight is one of our most powerful senses. It feels trustworthy, direct, reliable. Then science began exposing its limitations. The process happened gradually. First came experiments demonstrating that sunlight contains invisible components. Then came discoveries showing that radiation exists beyond both ends of the visible spectrum. Later came instruments capable of detecting those invisible forms of energy. Each new discovery expanded humanity's window onto the universe, and each expansion revealed the same thing. Reality was much richer than it appeared. Astronomers quickly realized this lesson applied to the cosmos as well. Visible stars represented only part of the story. The universe contained vast quantities of hidden light. Light that existed, light that traveled through space, light that carried information, light that human eyes simply could not perceive. This realization transformed astronomy. Before long, scientists began building telescopes designed to observe wavelengths beyond ordinary vision. The results were astonishing. Regions of space that appeared dark suddenly lit up. Structures invisible in visible light became obvious. Entire categories of cosmic objects emerged from hiding. The universe turned out to be far more active than anyone suspected. Let's begin with infrared light. Infrared wavelengths are longer than visible red light. Human eyes cannot detect them. Yet warm objects constantly produce infrared radiation. Your body is producing infrared radiation right now. So is your chair. So is the room around you. Special cameras can detect this invisible glow and convert it into visible images. What appears dark to your eyes often appears bright in infrared. Astronomers quickly discovered that the same principle applies in space. Some regions of the cosmos hidden behind thick clouds of dust become visible when observed in infrared wavelengths. Visible light struggles to penetrate the dust. Infrared radiation passes through more easily. Suddenly, astronomers could peer into places previously concealed. Stellar nurseries appeared. Newborn stars emerged from hiding. Entire structures inside galaxies became visible for the first time. The darkness began retreating. Then came radio astronomy. Radio waves possess wavelengths far longer than visible light. Some stretch for meters, others stretch for kilometers. Human eyes are completely blind to them, yet the universe generates radio waves continuously. When radio telescopes started surveying the sky, astronomers encountered another surprise. Objects invisible through ordinary telescopes suddenly appeared. Powerful radio galaxies, enormous clouds of hydrogen gas, exotic remnants of stellar explosions, entire populations of cosmic structures previously unknown. Again, the lesson repeated itself. Darkness was not necessarily emptiness. Sometimes it merely reflected the limitations of human vision. One particularly fascinating example involves hydrogen. Hydrogen is the most abundant element in the universe. It fills vast regions of interstellar space. Most of it remains invisible to human eyes. Yet hydrogen naturally emits radio waves under specific conditions. Using radio telescopes, astronomers can map enormous hydrogen clouds stretching across galaxies. Regions that seem empty in visible light often reveal intricate structures when observed through radio astronomy. The darkness becomes populated, the emptiness disappears, the hidden universe emerges. X-rays revealed another surprise. These wavelengths possess much higher energies than visible light. Human eyes cannot detect them. Fortunately, otherwise medical imaging would be a very strange experience. In space, X-rays often originate from some of the most extreme environments imaginable. Black holes, neutron stars, superheated gas, violent cosmic collisions. Many of these objects appear inconspicuous through ordinary telescopes. Observe them using X-ray instruments, and they become dazzling beacons. Entirely new versions of the universe appear. It's almost like switching between different channels on a television. Each wavelength reveals different information. Each wavelength tells a different story. None provides the complete picture alone. Together, they create a much richer understanding of reality. One of the most important consequences of this realization involves our original question. Why is space so dark when stars are so bright? By now we're beginning to see that the question itself contains a hidden assumption. The assumption is that visible darkness equals actual darkness. That assumption turns out to be misleading. Space appears dark largely because human eyes detect only a narrow range of radiation. The universe contains vastly more light than we can directly perceive. Some of that light originated billions of years ago. Some originated yesterday. Some arrives from distant galaxies. Some arrives from structures within our own Milky Way. The sky's alive with invisible radiation. Our eyes simply don't participate in most of it. A useful comparison might be rain. Imagine standing beneath a roof while rain falls everywhere around you. You remain dry. Someone unfamiliar with the situation might conclude no rain exists. The conclusion would be understandable, but incorrect. The rain is real. Your position merely prevents you from experiencing it. Human vision occupies a similarly sheltered position. We detect only one small portion of the universe's electromagnetic activity. Most remains hidden, not because it isn't there, because evolution never gave us the tools to see it, and why would it? Our ancestors evolved on Earth's surface. Visible light provided enough information for survival. Detecting infrared galaxies or radio emissions from distant quasars offered little advantage when avoiding predators or searching for food. Nature optimized our senses for survival, not cosmology. As a result, the universe extends far beyond immediate perception. Astronomers learned this lesson repeatedly throughout the 20th century. Every time a new wavelength became accessible, unexpected discoveries followed. the invisible universe proved remarkably rich, remarkably complex, remarkably bright. Perhaps nowhere is this more dramatic than in the case of ancient starlight. Remember what we discussed earlier. Light travelling across expanding space becomes stretched. Visible wavelengths can gradually shift into infrared wavelengths. Continue stretching long enough, and the light eventually becomes microwaves. This means some of the oldest light in existence no longer appears visible at all, yet it still surrounds us. In fact, it fills the entire universe. That ancient radiation represents one of the greatest discoveries in scientific history. Its existence was predicted before it was observed. Then, during the 1960s, two radio astronomers named Arno Penzias and Robert Wilson stumbled upon an unusual signal. No matter where they pointed their antenna, the signal remained. They checked their equipment, they checked the atmosphere, they checked everything they could think of. Nothing eliminated the mysterious background radiation. Eventually they realized they had discovered something extraordinary. They were detecting ancient light left over from the early universe. Not visible light, microwave radiation, light that had been stretched by billions of years of cosmic expansion. Today we call it the cosmic microwave background. The discovery fundamentally changed cosmology. It provided powerful evidence for the universe's early history. But for our discussion tonight, it teaches another important lesson. The sky is not truly dark. Even in apparently empty directions, ancient radiation fills space. Our eyes simply fail to detect it. If human vision extended into microwave wavelengths, the night sky would look dramatically different. Instead of darkness, we would perceive a faint glow surrounding us in every direction. Not bright enough to rival the sun, not bright enough to illuminate landscapes, but present, persistent, a relic from the universe's youth. The darkness overhead would never seem quite as empty again. As technology improved, astronomers uncovered more examples. Infrared observatories revealed galaxies hidden behind cosmic dust. Radio telescopes mapped gigantic structures invisible to optical instruments. Space-based observatories detected X-rays and gamma rays from violent cosmic events. Each discovery reinforced the same message. The universe contains far more light than visible astronomy alone suggests. The night sky is like a book with most of its pages written in invisible ink. The information exists. You simply need the right tools to reveal it. And once those tools arrived, astronomers began recognizing that many apparently dark regions contain enormous quantities of matter and energy. What seemed empty often proved surprisingly crowded. What seemed silent often proved remarkably active. The hidden universe became impossible to ignore. This realization also changes the emotional experience of looking upward. The dark sky no longer feels quite so empty. Every patch of blackness may conceal infrared galaxies, radio-emitting hydrogen clouds, ancient microwave radiation, invisible streams of energy crossing the cosmos. The darkness becomes less like a void and more like a veil, something that hides rather than eliminates, something that conceals rather than erases. Across much of human history, dust had a terrible reputation. Dust gathered on shelves, dust covered forgotten objects, dust drifted into homes and settled on furniture no matter how often people cleaned. Nobody looked at a dusty room and thought, this is one of the most powerful forces shaping the appearance of the universe. Yet astronomy has a way of turning ordinary things into extraordinary ones. The same substance that collects beneath your bed helps determine what we see when we look across entire galaxies. The same tiny particles that float through sunlight can influence observations spanning thousands of light years. And when astronomers began studying the darkness of space, they eventually discovered that dust and gas were playing an important role, not the entire role. As we've already seen, the finite age of the universe matters. The expansion of space matters, redshift matters, the limits of human vision matter, but cosmic dust and gas add another layer to the story. They help create some of the most dramatic shadows in existence, shadows so large they can stretch across vast portions of galaxies, shadows so immense that they make planetary distances seem tiny by comparison. To appreciate their impact, let's begin with something familiar. Imagine standing outside on a sunny afternoon. A cloud drifts in front of the sun. The brightness around you changes immediately. Nothing happened to the sun itself. The sun continues producing enormous amounts of light. The change occurred because something moved between you and the source of illumination. The cloud blocked part of the light. The same principle operates throughout the cosmos. Light rarely travels through perfectly empty space. Instead, it often encounters gas and dust scattered between stars. These materials can absorb light, scatter light, redirect light, transform the appearance of entire regions of the universe. The effect becomes particularly important because the distances involved are so enormous. A small amount of material stretched across hundreds of light years can have a dramatic impact on what astronomers observe. When people hear the word dust, they often imagine something substantial. Perhaps grains of sand, tiny specks visible to the naked eye. Cosmic dust is usually much smaller. Many particles are comparable in size to smoke particles. Others are even smaller. Individually, they seem insignificant. Collectively, they become powerful. Imagine holding a single grain of dust between your fingers. It appears harmless. Now imagine trillions upon trillions of such particles floating through space, spread across regions larger than entire solar systems. The cumulative effect becomes impossible to ignore. Astronomers first encountered this reality while studying the Milky Way. At first glance, our galaxy appears as a pale, luminous band stretching across the sky. For thousands of years, people admired its beauty without fully understanding its nature. Eventually, telescopes revealed the truth. The Milky Way is not a cloud, it is a galaxy, a vast collection of stars viewed from within. But astronomers noticed something peculiar. Certain regions seemed dark. Not dark because stars were absent. Dark because something blocked the starlight. Huge dark lanes cut across portions of the Milky Way. Gigantic shadows interrupted the glow. At first, some observers wondered whether these regions might simply contain fewer stars. Perhaps the galaxy possessed gaps, empty zones, places where stars never formed. Further observations revealed a different explanation. The stars existed. We simply couldn't see them. Enormous clouds of dust lay between Earth and those distant stellar populations. The dust absorbed and scattered visible light. The result was a cosmic silhouette, a shadow stretching across space. One of the most famous examples is the region known as the Great Rift. This enormous collection of dark dust clouds divides portions of the Milky Way visible from Earth. To the naked eye, parts of our galaxy appear split by darkness. The effect is so striking that many ancient cultures incorporated these dark regions into their stories and constellations. What looked like emptiness turned out to be the opposite. Dense concentrations of material block the view. The darkness was created by abundance rather than absence. Astronomy repeatedly returns to this theme. Things that appear empty often aren't. Things that appear dark often hide something. The universe enjoys misleading first impressions. Dust provides one of its favourite tricks. Consider what happens when light encounters a dust cloud. Some photons pass through, others are scattered, others are absorbed entirely. The cloud behaves like a gigantic filter. The farther light must travel through that material, the stronger the effect becomes. This phenomenon is known as extinction, a somewhat dramatic name, but an accurate one. The dust effectively extinguishes part of the light before it reaches observers. As a result, distant stars appear dimmer than they otherwise would, sometimes much dimmer. In extreme cases, entire stellar populations can vanish from visible view. Yet those stars continue shining. The darkness exists only because something lies between them and us. One useful comparison involves fog. Imagine driving through thick fog at night. Headlights become weaker, distant objects fade, streetlights appear blurred and diminished. The fog doesn't eliminate the light, it interferes with its journey. Cosmic dust behaves similarly on a vastly larger scale. Entire regions of galaxies can be obscured. Structures spanning hundreds of light years can disappear. Darkness emerges from interference rather than emptiness. Gas contributes as well. Although gas is often more transparent than dust, enormous clouds of interstellar gas populate galaxies throughout the universe. These clouds consist primarily of hydrogen and helium, the same basic ingredients that helped build stars in the first place. Under certain conditions, gas can absorb specific wavelengths of light. Astronomers actually use this property to learn about distant regions of space. As light passes through intervening gas clouds, characteristic signatures appear in the spectrum. The gas leaves fingerprints. Invisible structures reveal their presence through the light they modify. Even when astronomers cannot see the cloud directly, they can often detect its influence. It's a little like noticing footprints in snow. You may not see the person who made them. You still know someone passed through. The universe leaves clues everywhere. Dust and gas leave particularly useful ones. There's another fascinating consequence of cosmic dust. While dust often blocks visible light, it also absorbs energy. And absorbed energy doesn't simply disappear. The dust warms up. Then it radiates energy of its own, usually in infrared wavelengths. This creates an interesting situation. A region that appears dark through an optical telescope may glow brightly through an infrared telescope. The darkness becomes illumination. The shadow becomes visible. The object that concealed light begins producing light. Astronomers frequently exploit this effect. Infrared observatories can peer through dust clouds that block ordinary vision. Regions hidden in visible light suddenly emerge. Entire stellar nurseries become visible. Young stars appear where darkness once dominated. The transformation can be dramatic. Images of the same region taken in different wavelengths sometimes look almost unrelated. One version appears dark and empty. The other reveals extraordinary complexity. The difference lies entirely in how the light is observed. This is one reason modern astronomy depends on multiple types of telescopes. Visible light alone tells only part of the story. To understand the universe fully, astronomers must examine every available wavelength. Each reveals different information. Each uncovers different structures. Each exposes different aspects of reality. Without infrared observations, many regions of the cosmos would remain hidden. Without radio observations, enormous hydrogen clouds would remain invisible. Without X-ray observations, some of the universe's most energetic phenomena would go unnoticed. The hidden universe is vast. Dust and gas often act as its gatekeepers. Perhaps the most beautiful examples involve star formation. Stars are born inside giant molecular clouds. These immense structures contain gas, dust, and raw material for future stellar systems. Viewed through ordinary telescopes, many appear as dark patches against brighter backgrounds. At first glance, they look empty. Look deeper, and a completely different picture emerges. Within those dark clouds, gravity slowly gathers material. Regions become denser. Temperatures rise. Eventually new stars ignite. Entire stellar populations begin their lives hidden inside cosmic shadows. The darkness conceals creation. One of the most famous examples is the Horsehead Nebula. Visible photographs show a striking dark silhouette against a brighter background. The shape resembles a horse's head rising from cosmic fog. It appears almost black, almost empty. Yet astronomers know the region contains enormous amounts of material: gas, dust, complex chemistry, potential future stars. The darkness itself is evidence of substance. Without the material, no shadow would exist. Similar stories unfold throughout the Milky Way. dark nebulae, molecular clouds, dust lanes, gigantic structures sculpting the appearance of galaxies. Some stretch across hundreds of light years, others span thousands. Together they create many of the shadows visible throughout the cosmos. And those shadows matter for our original question. Why is space so dark when stars are so bright? Part of the answer involves these galactic veils. Light does not travel unchallenged. Along its journey it encounters material. The material absorbs, scatters, and modifies the radiation. Some brightness never reaches us. Some wavelengths are filtered out. Some regions disappear behind immense curtains of dust. The darkness increases. Yet astronomy also teaches us not to exaggerate their role. For many years, people hoped dust alone might solve the darkness puzzle completely. As we discussed earlier, that explanation ultimately failed. Dust absorbs light, but absorbed energy eventually reappears as radiation. The universe keeps careful track of energy. It rarely allows easy disappearances. Dust contributes to darkness. It does not create all of it. Instead, it works alongside other factors: finite age, finite light speed, expansion, redshift, hidden wavelengths, cosmic shadows. Each contributes part of the answer. The full explanation emerges only when all the pieces come together. What makes this especially fascinating is how often darkness turns out to be misleading. A dark region may contain stars. A dark region may contain gas. A dark region may contain dust. A dark region may contain active star formation. A dark region may contain ancient radiation. Again and again, astronomy discovers that apparent emptiness conceals complexity. The darkness above us becomes less like a void and more like a mask hiding structures beyond immediate perception. And yet, even after accounting for hidden light and cosmic shadows, another question remains. What about the enormous regions between stars themselves? What about the vast stretches of space where neither bright stars nor thick dust clouds dominate? Consider the nearest star beyond our Sun, not a distant galaxy, not an object at the edge of the observable universe, just the closest neighbouring star. Its name is Proxima Centauri, and even though it occupies our cosmic backyard, its light requires more than 4 years to reach Earth. 4 years, travelling at the fastest speed known in nature. The speed of light is so extraordinary that it can circle our planet more than 7 times in a single second. Yet even that incredible speed needs over 4 years to cross the gap separating us from the nearest star. That fact alone tells us something important. Space is astonishingly empty. When people first learn astronomy, they often focus on the objects, the stars, the planets, the galaxies. The nebulae. Those things naturally attract attention because they're bright, beautiful, and visually striking. But the real story of the universe is often found in what lies between them. The emptiness, the distances, the vast regions where almost nothing exists at all. And as strange as it sounds, this emptiness plays a major role in explaining why space appears dark. Because one of the biggest reasons darkness dominates the sky is that the universe contains far more space than stars. Far more. To appreciate how dramatic this imbalance really is, let's start close to home. Imagine shrinking the sun until it becomes the size of a basketball. Not a giant beach ball, not a car, just an ordinary basketball. On that scale, Earth would be about the size of a small pea, and where would that pea be located? Perhaps a few meters away, across the room, not even close. The pea would sit roughly 26 meters away, almost the length of a basketball court. Between the basketball sun and the pea Earth would be mostly empty space. Nothing, just emptiness. Already our solar system starts looking surprisingly vacant, and it gets even stranger. Where would Neptune be? The outermost major planet. On this scale, Neptune would orbit nearly 800 meters away, almost half a mile from the basketball sun. Again, almost all of that distance would consist of empty space. The planets themselves occupy almost none of the volume. The solar system is largely a giant region of nothingness with a few objects sprinkled throughout. Yet compared with the distances between stars, the solar system is compact. Let's return to our basketball sun. Where would the nearest star be? Not a few kilometers away. Not even a few dozen kilometers away. The nearest star would be approximately 7,000 kilometers distant. Roughly the distance from New York to Paris. Imagine placing a basketball in one city and another basketball-sized star thousands of kilometers away. Everything between them would be essentially empty. That's the true nature of stellar neighborhoods. Stars aren't packed together like streetlights along a road. They're separated by enormous gulfs of space, dark, quiet, mostly empty. The night sky can sometimes create a misleading impression. Look upward, and stars appear scattered everywhere. Thousands of bright points seem to fill the heavens. It almost resembles a glittering blanket. But that's an illusion created by perspective. The stars only appear crowded because they are viewed against a distant background. In reality, they are separated by extraordinary distances. If you could somehow travel through our local region of the Milky Way, you might spend years crossing empty space before encountering another star. The galaxy is not a dense forest. It is more like a vast desert with occasional islands. The darkness between stars is not a small feature of the universe. It is the dominant feature. Let's think about our own galaxy for a moment. The Milky Way contains hundreds of billions of stars. That sounds crowded. It sounds like a place overflowing with celestial objects. Yet the Milky Way is roughly 100,000 light-years across. The volume involved is almost impossible to comprehend. Even hundreds of billions of stars become sparse when distributed throughout such an enormous structure. Imagine placing a few hundred grains of sand inside a gigantic sports stadium. The number of grains sounds impressive until you compare it to the size of the stadium. Suddenly the space dominates. The stars are like those grains. The galaxy is the stadium. Most of what exists between stars is simply empty space. Not perfectly empty, of course. Astronomers rarely use the word empty literally. There are occasional atoms, tiny traces of gas, the occasional dust particle, magnetic fields, radiation passing through. But compared with earthly standards, the emptiness is extreme. A laboratory vacuum created by scientists still contains vastly more particles than many regions of interstellar space. In some areas of the galaxy, you might find only a few atoms per cubic centimetre. A volume the size of a sugar cube could contain less matter than the surrounding air contains in a fraction of a blink. The universe is remarkably good at making emptiness. This emptiness contributes directly to darkness. After all, darkness isn't just about the absence of light sources. It's also about the enormous distances separating those sources. Think about a city at night. Suppose every building contains lights. From an airplane, the city glows. The lights overlap. They blend together. Darkness retreats. Now imagine spreading those same buildings across an entire continent. The lights become isolated. Vast dark regions appear between them. The total number of lights remains unchanged. The spacing changes everything. The universe operates similarly. Stars are bright. Many stars exist, but they are separated by such immense distances that darkness dominates the regions between them. The emptiness wins, at least visually. This realization helped astronomers understand another aspect of Olbers's paradox. The paradox correctly pointed out that an infinite eternal universe filled uniformly with stars should appear bright. But the actual universe isn't simply a featureless collection of evenly distributed stars. Structure matters. Distribution matters. Distance matters. The cosmos possesses enormous regions where stars are relatively sparse, enormous regions where darkness naturally dominates. And as astronomers looked farther from individual stars, they discovered something fascinating. The darkness between stars is not merely a passive background. It influences how galaxies behave. It shapes the evolution of cosmic structures. It provides the environment in which stellar systems exist. Without those vast empty regions, the universe would look entirely different. In fact, life itself might be impossible. Imagine a galaxy where stars sat much closer together. The night sky would certainly be brighter, but planetary systems would experience constant gravitational disturbances. Orbits could become unstable. Close stellar encounters would occur more frequently. The calm environment that allowed Earth's history to unfold might never have existed. The emptiness between stars provides stability. The darkness serves a purpose. That's a recurring theme in astronomy. Features that initially seem disappointing often turn out to be essential. Darkness isn't merely something missing. Darkness is part of the architecture of the cosmos. The vast gaps between stars create room for planetary systems, room for galaxies to evolve, room for cosmic history to unfold. Yet even after accepting the immense emptiness between stars, the scale of the universe remains difficult to grasp. Because stars are only one level of structure, galaxies themselves are separated by even larger distances. Let's leave the Milky Way for a moment. Our nearest major galactic neighbour is the Andromeda Galaxy. It's approximately 2.5 million light-years away. Light leaving Andromeda, when early human ancestors were first learning to use simple stone tools, is only reaching us now. Between the Milky Way and Andromeda lies an enormous volume of mostly empty space, a darkness so vast that ordinary language struggles to describe it. Yet Andromeda is considered nearby. Nearby. That single word reveals how extreme astronomy can become. As astronomers mapped larger regions of the cosmos, they found galaxies organised into groups, groups organised into clusters, clusters organised into superclusters, and between those structures lay even greater voids, cosmic voids, regions so immense they make galaxies seem tiny. Some cosmic voids stretch hundreds of millions of light-years across. Within them, galaxies become extraordinarily rare. The darkness reaches almost unimaginable scales. If you lived inside one of these voids, the night sky might look very different. Galaxies would be fewer. The cosmic landscape would appear lonelier. The emptiness would become even more dominant. The discovery of cosmic voids revealed something surprising. The universe resembles a gigantic web. Galaxies cluster along filaments and nodes, leaving enormous empty regions between them. Astronomers call this structure the cosmic web. It's one of the largest patterns known to exist, and much of it consists of emptiness. Again and again, observations point toward the same conclusion. The universe is not primarily made of stars. It is not primarily made of planets. It is not primarily made of galaxies. The universe is primarily made of space, vast regions of space, overwhelming regions of space. The objects attract our attention. The emptiness dominates the volume. That imbalance helps explain why darkness remains so powerful. Even though stars generate extraordinary amounts of light, the sheer scale of the emptiness between them dilutes their influence. The universe is simply too large. The gaps are too enormous. The darkness has room to survive. There is also a psychological aspect to this story. Humans evolved in environments where empty space rarely reaches extreme scales. Walk across a field, cross a valley, sail across an ocean. Even our largest earthly distances remain tiny compared with cosmic ones. As a result, our intuition struggles with astronomical emptiness. We instinctively underestimate it. We imagine stars closer together than they really are. We imagine galaxies packed more tightly than they actually are. Reality consistently exceeds those expectations. The cosmos is far emptier than common sense suggests, and that emptiness becomes visible every night, every dark patch between stars. Every black region separating constellations, every area where no bright object appears, all of it reflects the extraordinary spaciousness of the universe. The darkness is partly a monument to scale, a reminder that space truly earns its name. If the universe contains so much darkness, so much hidden light, so much space between stars and galaxies, how bright is the cosmos overall? After accounting for redshift, distance, hidden radiation, and immense cosmic voids, what would happen if we could somehow measure all the light in the universe at once? Suppose someone handed you a magical dimmer switch. Not a switch connected to a lamp, not a switch connected to a house, a switch connected to the entire universe. Turn it one way and every star, every galaxy, every glowing cloud of gas would become brighter. Turn it the other way and everything would gradually fade. Now imagine standing outside beneath a perfectly dark sky and asking a simple question. Where is the switch currently set? Which? Is the universe actually bright, or is it fundamentally dark? At first the answer seems obvious. Look upward on a clear night and darkness dominates almost everything. Most of the sky appears black. Stars occupy only tiny points. The overwhelming impression is one of emptiness and darkness. Yet as we've discovered throughout this journey, first impressions can be misleading. The universe contains far more light than human eyes reveal. Ancient radiation fills space. Galaxies produce enormous amounts of energy. Stars shine continuously across billions of years. Even regions that appear dark often contain invisible wavelengths beyond human vision. The deeper astronomers looked, the stranger the question became. Maybe the universe wasn't as dark as it seemed. But if that's true, another question immediately follows. Just how bright is it? The answer turns out to be surprisingly difficult to determine. After all, brightness depends on perspective. Stand beside a campfire and it feels dazzling. View the same campfire from an airplane and it becomes almost invisible. The campfire hasn't changed, your position has. The universe presents a similar challenge. Astronomers needed a way to measure the total amount of light produced throughout cosmic history. Not merely the light from nearby stars, not merely the light visible to human eyes, all of it. Every wavelength, every galaxy, every source. Only then could they begin answering a surprisingly profound question. How much illumination does the universe actually contain? To appreciate the scale of the problem, let's start with our own galaxy. The Milky Way contains hundreds of billions of stars. Many are dimmer than the Sun, many are brighter. Together they generate an astonishing amount of energy. If you could somehow travel far beyond the Milky Way and view it from a distance, it would appear as a luminous spiral island floating in darkness. Beautiful, bright. Easy to spot across vast distances. Now remember that the observable universe contains not one galaxy. It contains hundreds of billions of them. Perhaps more. Every galaxy packed with stars. Every star producing light. Every second. Every minute. Every year. The total amount of energy involved is difficult to comprehend. It is so large that ordinary comparisons quickly fail. Imagine trying to count every grain of sand on every beach on Earth. Then imagine discovering that your estimate was still too small. The universe specializes in scales that exceed intuition. Yet despite this overwhelming abundance of light, something surprising happens when astronomers calculate the average brightness of the cosmos. The universe is not particularly bright. In fact, averaged across enormous volumes of space, it is remarkably dim. This sounds contradictory at first. How can a universe containing trillions upon trillions of stars be dim? The answer returns us to something we've encountered repeatedly. Distance, space, emptiness. The stars themselves are bright. The gaps between them are immense. Imagine placing 1,000 powerful floodlights inside a gigantic stadium. The floodlights shine brilliantly. But if the stadium were expanded until it became the size of a continent, the average brightness would drop dramatically. The lights would remain powerful. The space between them would dominate. The universe behaves similarly. Stars produce tremendous amounts of energy, yet the volume of space is so enormous that the average brightness remains surprisingly low. Astronomers have actually attempted to quantify this. One famous effort involved measuring what is known as the cosmic optical background. Think of it as a kind of accounting system for starlight. Scientists attempted to estimate all the visible light produced by stars throughout cosmic history, not just nearby stars, all stars, across the observable universe. The result was fascinating. The universe contains an enormous amount of cumulative starlight, far more than any individual observer experiences. Yet spread across the colossal volume of the cosmos, the brightness becomes surprisingly gentle. In a sense, the universe is both bright and dim simultaneously, bright in total output, dim in average appearance. Another way to think about it involves cities at night. Imagine flying above Earth after sunset. Individual cities shine brilliantly. Major metropolitan regions produce spectacular displays of light, yet between those cities lie vast dark regions, forests, deserts, mountains, oceans. If you average everything together, darkness still occupies most of the planet. The universe follows a similar pattern. Galaxies function like cosmic cities. They shine intensely. The spaces between them dominate the larger picture. This creates an interesting paradox of perception. Human eyes tend to focus on bright objects. We notice stars. We notice galaxies. We notice glowing nebulae. Our attention naturally gravitates towards sources of illumination. As a result, we sometimes underestimate the amount of darkness surrounding them. The darkness is not merely background scenery. The darkness is the majority. Imagine taking every star visible from Earth and compressing them into a single region of the sky. The result would certainly be brighter, perhaps dramatically brighter. Yet even then, the universe beyond that concentrated patch would remain vast and dark. The scale of cosmic emptiness is difficult to overcome. There is another factor complicating the calculation. Not all stars shine forever. Stars are born. Stars age. Stars die. The universe continuously changes its inventory of light sources. Some stars exhaust their fuel and fade. Others explode as supernovae. New stars ignite inside molecular clouds. The cosmic population evolves over time. This means the brightness of the universe has not remained constant throughout history. There were periods when star formation occurred more rapidly, periods when galaxies produced new stars at astonishing rates. Astronomers sometimes refer to a time known as cosmic noon. Several billion years after the universe began, star formation reached a particularly active phase. Galaxies were producing stars far more vigorously than they do today. If intelligent observers had existed then, they might have seen a somewhat brighter cosmos, not dramatically brighter, but different, more active, more luminous. Since that era, star formation has gradually declined. The universe still produces new stars. It simply does so at a slower pace. In some sense, the cosmos has become calmer with age. The great fireworks display of stellar creation has eased. This realization introduces a fascinating possibility. The universe may have experienced its brightest era in the distant past. Not because individual stars were brighter, but because more stars were being born, more galaxies were actively producing light. The overall cosmic glow may have been stronger. Today we inhabit a somewhat quieter universe, a mature universe, a universe where many galaxies have settled into slower rhythms. Even so, the amount of light remains extraordinary. Consider the sun alone. Every second, the sun converts millions of tons of matter into energy. Every second. And it has been doing this for billions of years. Now multiply that process by hundreds of billions of stars inside the Milky Way. Then multiply again by hundreds of billions of galaxies. The resulting numbers become almost absurd. The universe is conducting a light show on a scale beyond imagination. Yet because of distance and expansion, much of that brilliance never reaches us in its original form. One of the most intriguing measurements ever attempted involved estimating the average colour of the universe. Yes, astronomers actually tried to determine this. After analysing enormous numbers of galaxies, researchers concluded that the average visible colour of the universe resembles a pale beige or cream colour. The result received the charming nickname cosmic latte. It's one of those delightful moments where science sounds unexpectedly whimsical. The entire visible universe, averaged together, appears roughly the colour of the weak coffee mixed with milk. Of course, no observer would actually see the sky that way. The light is far too diluted, the darkness far too dominant. Yet the calculation reveals something important. The universe is not fundamentally black. The blackness we observe emerges from perspective, distance, and the distribution of light. The underlying reality contains immense luminosity. There is also the matter of hidden light. As we've discussed, visible radiation represents only a tiny fraction of the electromagnetic spectrum. Many galaxies emit enormous quantities of infrared radiation. Others produce radio waves. Some generate powerful X-rays. If human eyes could perceive all wavelengths simultaneously, the night sky would appear dramatically different. Regions currently dark would brighten. Invisible structures would emerge. The universe would feel much busier, much more crowded. The darkness would retreat. This doesn't mean the cosmos would become blindingly bright. The vast emptiness would still exist. The distances would remain enormous, but our perception of darkness would change significantly. We would discover that much of what appears empty is actually alive with activity. Signals crossing space, radiation flowing between galaxies, ancient photons continuing journeys billions of years long. The universe would reveal itself as a place saturated with information. And yet, perhaps the most remarkable conclusion is this. Despite all the light ever produced by stars, galaxies, and other cosmic phenomena, darkness still wins. Not because darkness is stronger, not because stars are weak, because the universe is vast, truly vast. The volume of space grows faster than our intuition can comfortably grasp. No matter how many stars exist, the emptiness remains overwhelming. The darkness survives because there is simply so much room for it. This balance between light and darkness may actually be one of the defining characteristics of the cosmos. Too little light and galaxies never form. Too much light and the night sky loses its mystery. Instead, the universe occupies a fascinating middle ground, bright enough to create stars, planets, and life, dark enough to preserve enormous cosmic vistas, bright enough to illuminate, dark enough to inspire curiosity. Long before the Earth existed, long before the sun began shining, and long before the first galaxies scattered themselves across the cosmos, the universe looked nothing like it does today. No stars, no planets, no constellations, no dark sky. In fact, if someone could somehow travel back to those earliest times and look around, they would encounter something that might seem surprising after everything we've discussed. They would not see darkness at all. They would see light everywhere. Not starlight, not galaxy light. Something even older, something more fundamental, the oldest light in existence, the first great illumination of the cosmos. And remarkably, traces of that ancient light still surround us today. Even now, even here, even as you listen to these words. The story begins near the beginning of the observable universe itself. Now, whenever scientists discuss the Big Bang, it's important to clear up a common misunderstanding. The Big Bang was not an explosion in space. It wasn't a giant fireball expanding into an empty void. There was no central point from which matter blasted outward like shrapnel from a cosmic grenade. Instead, the Big Bang describes the early expansion of space itself. Every region of the observable universe was once compressed into an extraordinarily hot, dense state. Then space began expanding, and it has continued expanding ever since. The earliest moments remain mysterious. Physics can describe much of what happened shortly afterward, but the first fractions of a second remain an area of active research. Even so, astronomers have assembled an increasingly detailed picture of what the young universe was like, and one thing is clear: it was incredibly hot. Temperatures reached levels difficult to imagine, not thousands of degrees, not millions, far beyond that. The universe was so energetic that atoms could not exist. Matter behaved very differently from anything familiar in everyday life. Particles collided constantly. Radiation flooded every direction. The cosmos resembled a brilliant, glowing ocean of energy. Darkness had no place there. The entire observable universe was filled with light. This might seem strange at first. After all, stars didn't exist yet. Galaxies didn't exist yet. So where did the light come from? The answer lies in temperature. Anything hot emits radiation. A campfire glows. Molten metal glows. The sun glows. The early universe was vastly hotter than any of those examples. As a result, it radiated enormous amounts of energy. The young cosmos itself was luminous, not because stars illuminated it, because everything was hot enough to glow. Imagine heating an iron rod. At first, it remains dark. Increase the temperature and it begins glowing red. Heat it further and it becomes orange, then yellow, then nearly white. The hotter it becomes, the brighter it shines. Now imagine heating not an iron rod, but the entire universe. That's roughly what existed during the earliest eras. A brilliant sea of radiation extending in every direction. Yet despite all this light, there was a problem. The universe was so dense that the light couldn't travel very far. Photons continuously collided with particles. Every attempt to move through space ended almost immediately in another interaction. The cosmos resembled a thick fog, a very bright fog, but a fog nonetheless. Imagine trying to shine a flashlight through dense clouds. The light exists, the brightness exists, yet visibility remains limited. The beam gets scattered again and again. The early universe behaved similarly. Radiation filled everything. But photons could not move freely. For hundreds of thousands of years, this situation continued. The universe expanded, temperatures gradually decreased, density slowly dropped, conditions changed, and eventually a crucial moment arrived. Astronomers call it recombination. The name sounds technical, but the basic idea is surprisingly simple. As the universe cooled, electrons could finally combine with atomic nuclei to form stable atoms. Before this happened, free electrons scattered light constantly. Afterward, most of those free electrons disappeared into atoms. Suddenly, photons could travel much greater distances. The cosmic fog cleared. Light was released. For the first time, the universe became transparent. This moment represents one of the most important transitions in cosmic history. Before it, the universe was opaque. After it, light could move freely across space, and some of that light is still travelling today. Think about that for a moment. Photons released when the universe was only about 380,000 years old continue crossing the cosmos. They have been travelling for nearly 13.8 billion years, through expanding space, past forming galaxies, past exploding stars, past the birth of the sun, past the emergence of life on Earth, still moving, still carrying information, still telling the story of creation. Those photons form what astronomers call the cosmic microwave background, often abbreviated as the CMB. It is one of the most extraordinary discoveries ever made, not because it's dramatic, not because it's bright, quite the opposite. The cosmic microwave background is incredibly faint. Yet hidden within that faint glow lies a direct record of the early universe. To understand how remarkable this is, imagine finding a photograph taken shortly after your birth. Not a written description, not a story passed down through generations, an actual photograph. Now imagine finding a photograph of the universe as an infant. That's essentially what the cosmic microwave background provides. A snapshot of the cosmos when it was extraordinarily young, the oldest light humanity has ever observed. The existence of this ancient radiation was predicted before it was discovered. By the middle of the 20th century, several physicists realized that if the universe began in a hot, dense state, traces of that heat should still remain. The expansion of the universe would cool the radiation dramatically, but not eliminate it. Some faint glow should persist. The prediction was bold. The challenge was finding it. Then, during the 1960s, an unexpected discovery changed everything. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large radio antenna. They kept detecting a faint background signal. No matter where they pointed the instrument, the signal remained. They checked for equipment problems. They checked nearby sources of interference. They even cleaned bird droppings from the antenna, suspecting contamination. The signal persisted. Eventually they realized something astonishing. They had discovered the cosmic microwave background, the ancient light predicted by theory, the faint afterglow of the early universe. It was one of the greatest scientific discoveries of the 20th century, because suddenly astronomers possessed direct evidence of the universe's hot beginning. The darkness of space was no longer merely darkness. Hidden within it was a faint microwave glow stretching across the entire sky. Not coming from one galaxy, not coming from one direction, coming from everywhere. The universe itself was glowing, very faintly, very quietly, but unmistakably. There is something almost poetic about this. The oldest light in existence surrounds us continuously, every moment of every day, every moment of every night, as you sit in your room, as you walk outside beneath the stars, as you look towards seemingly empty regions of space. Ancient photons pass through the Earth, through the atmosphere, through your body, carrying information from nearly the beginning of cosmic history. Yet human eyes cannot see them. Why not? Because expansion changed them. Remember redshift. Remember stretching. The light released during recombination was originally much more energetic, visible light and beyond. Over billions of years, the expansion of the universe stretched those wavelengths dramatically. The photons lost energy. The wavelengths grew longer. Eventually, the radiation moved into the microwave portion of the spectrum. The light remains. Its form changed. The universe transformed brilliant ancient radiation into a faint microwave glow. Without specialized instruments, we never would have known it existed. This discovery also reshaped our understanding of darkness. Recall the original question: why is space so dark when stars are so bright? The cosmic microwave background reveals that darkness can be deceptive. The night sky appears black, yet every direction contains radiation. Every direction contains ancient light. The darkness is not empty. The darkness is glowing, very faintly, just beyond the reach of human vision. Modern satellites have studied the cosmic microwave background in extraordinary detail. Missions such as COBE, WMAP, and Planck mapped this radiation with increasing precision. What they found was astonishing. The glow is almost perfectly uniform. Almost. Tiny variations exist. Extremely tiny. Differences amounting to fractions of a degree. Yet those tiny fluctuations turned out to be enormously important. They represent slight density variations present in the young universe. Regions with slightly more matter. Regions with slightly less. Over billions of years, gravity amplified those differences. The denser regions attracted more material. Galaxies formed. Clusters emerged. The cosmic web developed. In a very real sense, every galaxy we see today traces its ancestry back to those tiny irregularities visible in the cosmic microwave background, including the Milky Way, including the solar system, including Earth, including us. The oldest light doesn't merely show us the past. It helps explain how the present came to exist. That realization makes the cosmic microwave background more than a scientific curiosity. It becomes a bridge connecting modern reality to the earliest observable moments of cosmic history. And remarkably, all of this information arrives hidden inside what appears to be darkness. The night sky continues playing tricks on us. Again and again, apparent emptiness conceals extraordinary stories. Ancient starlight, invisible radiation, galactic shadows, cosmic expansion, and now the faint glow of creation itself. By this point, the darkness above us has become much more complicated than it first appeared. The black sky is not merely a lack of illumination, it is a layered record of cosmic history, a record written in light both visible and invisible. Several decades ago, an astronomer found himself facing a problem that shouldn't have existed. The observations were clear, the calculations were straightforward. The laws of gravity seemed well understood, and yet the universe refused to cooperate. Something invisible appeared to be influencing entire galaxies. Something unseen was pulling on stars. Something hidden was shaping the cosmos on scales so enormous that the consequences stretched across millions of light years. At first, the idea sounded ridiculous. After all, astronomy is built around light. Stars reveal themselves through light. Galaxies reveal themselves through light. Nebulae reveal themselves through light. For centuries, astronomers learned about the universe by studying things they could see. Then the universe presented a troubling possibility. What if most of reality couldn't be seen at all? What if light only told part of the story? And what if the darkness between the stars concealed far more than anyone imagined? By the time we reach this point in our journey, the night sky has already become much stranger than it first appeared. The darkness overhead is not simply empty space. We've discovered ancient radiation hidden beyond visible wavelengths. We've found enormous clouds of gas and dust. We've learned that cosmic expansion stretches light beyond human vision. We've seen that the universe contains immense distances separating stars and galaxies. Again and again, darkness has proven deceptive. Yet the next discovery would push that lesson even further. Because this time, astronomers weren't merely dealing with hidden light. They were dealing with something that seemed to produce no light at all. The story begins with galaxies. During the early 20th century, astronomers became increasingly skilled at measuring how galaxies rotate. At first glance, a galaxy looks fairly simple. A giant collection of stars orbiting a common centre, rather like planets orbiting the Sun. The expectation seemed obvious. Stars near the centre should move quickly. Stars farther away should move more slowly. The same basic pattern appears throughout the solar system. Mercury races around the Sun. Neptune moves much more slowly. Distance affects orbital speed. Gravity behaves predictably, or so everyone thought. Then astronomers started measuring actual galactic motions, and the results were deeply confusing. Stars near the outer edges of galaxies were moving much faster than expected, far faster. According to the visible matter present, many of those stars should have escaped entirely. They should have flown away into intergalactic space. Instead, they remained gravitationally bound. The galaxies held together. Something wasn't adding up. Imagine watching a merry-go-round spin. If it rotates too quickly, objects near the edge fly off. Now imagine the edge moving incredibly fast while everything somehow remains attached. You would immediately suspect hidden support structures. Something unseen must be holding things together. Astronomers reached a similar conclusion. The visible stars weren't providing enough gravity. There had to be additional mass that could not be seen, mass that produced no detectable light, mass hidden within the darkness. The idea seemed extraordinary, yet observation after observation pointed toward the same conclusion. Galaxies appeared much heavier than they looked, far heavier. The visible stars represented only a fraction of the total mass. Most of the matter seemed invisible. Astronomers eventually gave this mysterious substance a simple name: dark matter. The name sounds dramatic, almost like something from science fiction. In reality, it's surprisingly straightforward. Dark matter is called dark because it doesn't emit light. It doesn't reflect light. It doesn't absorb light in any significant way that we can detect. As far as our instruments can tell, it remains invisible, yet gravity reveals its presence. The universe keeps leaving fingerprints. Even when something refuses to shine, its gravitational influence can still be measured. And those measurements became increasingly difficult to ignore. The evidence accumulated from many directions. Galaxy rotation provided one clue. Galaxy clusters provided another. Clusters are enormous collections of galaxies bound together by gravity. When astronomers calculated the amount of visible matter inside those clusters, they encountered the same problem again. The numbers didn't work. The galaxies moved as though much more mass existed than telescopes could see. Visible matter alone couldn't explain the observations. The missing mass kept reappearing everywhere. Then came another remarkable discovery. According to Einstein's theory of general relativity, gravity can bend light. Massive objects distort space-time. As light passes nearby, its path changes. Astronomers call this gravitational lensing. Sometimes the effect creates distorted images of distant galaxies. Sometimes it creates arcs or rings. Sometimes it magnifies objects that would otherwise remain too faint to observe. Most importantly for our story, gravitational lensing allows astronomers to measure mass, not visible mass, total mass, whatever exists, visible or invisible. And once again the universe delivered the same message. There was far more mass present than telescopes could account for. Dark matter seemed to be everywhere, not concentrated inside stars, not concentrated inside planets, distributed throughout galaxies and clusters, forming enormous invisible structures, creating gravitational scaffolding on cosmic scales. One of the strangest realizations came when astronomers began estimating how much dark matter exists. The answer was surprising. Ordinary matter, the kind that forms stars, planets, oceans, trees, mountains, and people, appears to represent only a small fraction of the universe. A very small fraction. Everything familiar, everything visible. Everything we have ever directly observed, all of it combined accounts for only a minority of cosmic matter. Dark matter appears far more abundant. Think about that for a moment. Every star you've ever seen, every galaxy visible through a telescope, every mountain, every ocean, every living thing. Together they make up only part of the cosmic inventory. Most matter seems to belong to something invisible, something we cannot directly observe. The darkness became deeper than anyone imagined. Yet somehow the story gets stranger, because just as astronomers were coming to terms with dark matter, another surprise arrived. This surprise wasn't about matter at all. It was about the expansion of the universe. Recall what we discussed earlier. Space expands. Galaxies move apart over time. For much of the 20th century, scientists assumed gravity should gradually slow that expansion. The universe expands outward. Gravity pulls inward. Simple enough. The real question was how quickly the expansion might slow. Perhaps eventually it would stop. Perhaps the cosmos would begin contracting. Perhaps some balance would emerge. Then observations delivered another shock. The expansion wasn't slowing down. It was speeding up. The universe was accelerating. Imagine throwing a ball into the air. You expect gravity to slow it down. Now imagine watching the ball move faster and faster instead. You would immediately know something unusual was happening. Astronomers experienced a similar reaction. The accelerating expansion made little sense. Something seemed to be pushing space apart. Something seemed to be overcoming gravity on enormous scales. Again, the evidence accumulated. Again, observations pointed toward a conclusion nobody expected. And again, scientists needed a name. They called the mysterious phenomenon dark energy. Just like dark matter, the word dark doesn't mean evil or sinister. It simply means unknown, unseen, poorly understood. Dark energy appears to dominate the large-scale behavior of the universe. Current estimates suggest it represents the majority of the cosmos, not stars, not planets, not gas, not dust, not dark matter, dark energy, something we barely understand, something driving accelerated expansion, something hidden within the fabric of reality itself. At this point, the cosmic inventory becomes almost surreal. Ordinary matter represents only a small fraction. Dark matter represents a much larger fraction. Dark energy appears to dominate everything else. The familiar universe turns out to be a minority component. The vast majority remains invisible. Imagine reading a book and suddenly discovering you've only seen a few chapters while the rest remain sealed. That's roughly how modern cosmology feels. The more we learn, the more we realize how much remains hidden. This realization changes the meaning of darkness. Originally we asked why space appears dark despite the brightness of stars. The question seemed visual, a question about light. Now the discussion has expanded into something much larger. Darkness no longer refers merely to the appearance of the night sky. Darkness refers to the limits of human knowledge, the limits of observation, the hidden majority of the cosmos. In some sense, the universe is reminding us to be humble. For centuries, people assumed stars and galaxies represented most of reality. Then evidence suggested otherwise. Again and again, observations revealed hidden layers, invisible radiation, invisible matter, invisible energy. Reality kept extending beyond appearances. What's especially fascinating is that dark matter and dark energy were not invented to make theories work. Scientists didn't sit down and decide the universe needed mysterious ingredients. The evidence came first. The observations created the problem. The names came afterward. Astronomers would happily abandon dark matter tomorrow if a better explanation appeared. They would happily replace dark energy with something more complete if observation supported it. Science follows evidence wherever it leads. At the moment, the evidence points toward an astonishing conclusion. Most of the universe exists beyond direct human perception. This doesn't mean the cosmos is unknowable. Far from it. Astronomers continue learning more every year. New telescopes gather new information. New observations refine existing models. The mystery gradually becomes clearer. Yet the fundamental lesson remains. The darkness of space is not merely a backdrop behind stars. It contains hidden structures, hidden influences, hidden ingredients shaping cosmic evolution. The night sky appears simple until you start asking questions. Then layer after layer emerges. Ancient light, expanding space, invisible wavelengths, cosmic shadows, dark matter, dark energy. Each discovery reveals another level of complexity, and perhaps the most remarkable part is this. Once astronomers understood why the sky is dark, another fascinating thought emerged. What if the universe were different? What if it truly were infinite and eternal? What if stars had been shining forever? Would darkness survive at all? Or would the entire cosmos blaze with light from horizon to horizon? Imagine stepping outside tonight and looking up at the sky. The stars are gone. Not because they've disappeared. Not because clouds have hidden them. Not because the universe has somehow switched off. They're gone because you can no longer distinguish them. The entire sky glows. Every direction, every angle, every patch of space. No black background remains. No darkness separates one star from another. The heavens resemble an endless surface of light, a ceiling without gaps, a cosmic wall stretching forever. At first that image sounds strange, perhaps even a little unsettling. We're so accustomed to darkness between the stars that it's difficult to imagine anything else. The blackness feels natural, expected, permanent. Yet the original mystery we've been exploring throughout this journey began with precisely this possibility. Maybe the night sky shouldn't be dark. Maybe darkness itself is the surprising thing. And if the universe were different in certain ways, the sky above us could look dramatically different from the one we know. To understand why, we need to return to the idea that troubled astronomers for generations, Olbers's paradox. The question was simple. If the universe is infinite, if stars fill that universe, and if stars have been shining forever, why isn't the sky bright? By now we know the answer. The universe has a finite age, space expands, light takes time to travel, redshift stretches ancient radiation. All of these factors work together to preserve darkness. But suppose we remove them. Suppose we imagine a different cosmos, an infinite cosmos, an eternal cosmos, a universe with no beginning, no cosmic dawn, no first stars. No finite age, just endless time stretching backward forever. What would the sky look like then? The answer is surprisingly dramatic. Darkness would almost certainly disappear. Let's start with the simplest version of the thought experiment. Imagine a universe that has existed forever. Stars have always existed. Light has always been travelling. Every direction contains stars. The distribution extends infinitely. Now ask yourself a simple question. When you look into the distance, how far can you see? In our actual universe, there is a limit. Light has only had 13.8 billion years to travel. Eventually you reach regions whose photons haven't arrived yet. That limit helps preserve darkness. In an eternal universe, that limit disappears. Light has had infinite time to travel. Every possible photon that could reach you has already had enough time to arrive. The cosmic horizon vanishes. Immediately the night sky becomes much brighter. But the effect doesn't stop there. Remember the forest analogy that helped create Olber's paradox in the first place? Stand inside a forest extending forever. Every line of sight eventually encounters a tree. No matter where you look, no matter which direction you choose, something occupies the view. Now replace every tree with a star. In an infinite, eternal universe, every line of sight eventually ends at a stellar surface. Perhaps a nearby star. Perhaps a distant one, but eventually a star. And that changes everything, because every patch of darkness would be filled. The black spaces between stars would gradually disappear. Light would accumulate, layer after layer, distance after distance, until the sky glowed continuously. Imagine standing inside a gigantic hall whose walls are covered entirely with light bulbs. The individual bulbs eventually blur together. You stop noticing separate sources. Instead, the entire room becomes luminous. An infinite, eternal universe behaves similarly. Given enough stars and enough time, the distinction between individual points of light begins to vanish. The sky becomes a glowing surface, not unlike the visible surface of a star itself. This idea sounds almost absurd. After all, the night sky obviously isn't bright. Yet that's precisely why the paradox became so important. The logic seemed unavoidable. The observations contradicted it. Something had to give. Eventually astronomers realized it was the assumptions themselves. The universe is not eternal. The universe is not infinitely old. The darkness overhead provides evidence of that fact. In a strange way, every black patch of sky acts like a witness testifying that cosmic history had a beginning. Without that beginning, darkness becomes extremely difficult to explain. Let's push the thought experiment further. Suppose you lived in this eternal universe. What would daily life be like? Interestingly, there might not be a meaningful distinction between day and night. The sky would always contain enormous amounts of light. The familiar cycle of darkness and illumination could disappear entirely. Earthly life evolved under alternating periods of daylight and darkness. Many biological systems depend upon that rhythm. Sleep cycles, migration patterns, plant growth, countless behaviors developed in response to changing light levels. In an eternally bright universe, those patterns might never emerge. Life itself could evolve differently, or perhaps not evolve at all. It's fascinating how a seemingly abstract cosmological question can eventually connect back to something as personal as sleep. The darkness we often take for granted may owe its existence to the finite history of the cosmos. Without that history, even our nightly routines might be impossible. There is another consequence worth considering. An eternal universe filled with stars would contain far more accumulated energy than our universe currently displays. Every star continuously emits radiation. Over infinite time, that radiation adds up, and if nothing removes it, the total brightness keeps increasing. The universe becomes increasingly saturated with light. Imagine filling a bathtub with water while never allowing any to drain. Eventually the tub overflows. Similarly, an eternal universe continuously producing starlight risks becoming overwhelmed by accumulated radiation. The darkness struggles to survive. In many ways, the night sky acts like a cosmic accounting system. Every dark region tells us something about the balance between light production and cosmic history. The existence of darkness implies limits. Limits on age, limits on travel time, limits on how much light has reached us. Remove those limits and the accounting changes dramatically. The sky brightens. Another interesting feature emerges when we think about temperature. Suppose the sky truly glowed in every direction, not with isolated stars, with continuous brightness. What would that mean for planets? A bright sky carries energy. Energy affects temperature. The environment around such planets might become significantly warmer. Nighttime cooling could disappear. The distinction between direct starlight and background illumination would blur. The universe itself would function almost like a giant radiating surface. This idea actually influenced some early cosmological debates. Astronomers realized that an infinitely bright sky creates additional physical problems, not merely visual ones, thermal ones, energy balance ones. The universe would behave differently. The consequences extend beyond aesthetics. Brightness changes physics. Of course, real cosmology turns out to be more complicated. Even if the universe were infinite, expansion still matters. Redshift still matters. Energy can still be diluted. Modern discussions of Olber's paradox involve more than simple geometry. They involve the entire history of cosmic evolution. Yet the central lesson remains remarkably powerful. Darkness is evidence. The sky could have looked very different. The fact that it doesn't tells us something profound about reality. Sometimes science advances by studying what exists. Other times it advances by studying what doesn't. The darkness between stars belongs to the second category. Its existence carries information. Its persistence carries information. Its very presence reveals properties of the cosmos. This makes darkness surprisingly valuable. Imagine a detective investigating a mystery. One clue comes from what is found at the scene. Another clue comes from what isn't found. Both matter. The night sky functions similarly. The stars tell one story. The darkness tells another. Only by considering both can we understand the whole picture. There is a certain irony here. For most of human history, people focused on the stars. The bright objects naturally attracted attention. Constellations received names. Planets inspired myths. Comets generated excitement and fear. The darkness largely faded into the background, yet the darkness was carrying one of the most important messages all along. A message about the age of the universe, a message about cosmic expansion, a message about the limits of observable reality. The absence of light turned out to be just as informative as the light itself. Modern cosmology often feels like that. Again and again, seemingly ordinary observations conceal extraordinary implications. A faint shift in wavelength reveals expansion. A tiny temperature fluctuation reveals the seeds of galaxies. A dark night sky reveals the history of the cosmos. Reality leaves clues everywhere. We simply need to learn how to read them. And once astronomers learned to read the darkness overhead, they discovered something remarkable. The night sky wasn't merely a backdrop. It was evidence that the universe had a beginning, evidence that light has limits, evidence that cosmic history matters, In an infinite eternal universe, those clues would vanish. The sky would blaze with accumulated starlight. Darkness would lose. Instead, we inhabit a universe where darkness survives. A universe where light is abundant but not unlimited. A universe where history leaves visible traces. A universe where the black spaces between stars tell a story every bit as important as the stars themselves. There is something wonderfully strange about the fact that an ordinary night sky helped reveal some of the deepest truths humanity has ever discovered. Not a giant telescope, not a spacecraft travelling beyond the solar system, not an experiment involving billion-dollar machines, just darkness. The same darkness people have looked at for thousands of years. The same darkness visible from deserts, mountains, forests, islands, and city rooftops. The same darkness that quietly appears every evening as Earth rotates away from the sun. Most people never think much about it, and honestly, who could blame them? Darkness feels normal, expected, routine. When night arrives, we expect the sky to grow dark. When stars appear, we admire them. Then we continue with our lives. Yet hidden inside that familiar experience is one of the most remarkable scientific stories ever told, because the darkness above us is not merely an absence of light, it is evidence. Evidence that the universe has a history. Evidence that the universe changes. Evidence that the cosmos had a beginning. Evidence that light itself has limits. The more astronomers investigated the darkness, the more they discovered that it was quietly revealing the structure of reality itself. That realization may be the most surprising lesson from our entire journey. The night sky isn't dark because the universe failed to produce enough light. Quite the opposite. The universe is astonishingly bright. Stars shine throughout countless galaxies. Ancient radiation fills space. Exploding stars release unimaginable amounts of energy. Black holes can power structures larger than entire galaxies. The cosmos produces light on scales that exceed human imagination, and yet darkness remains. At first, that seems contradictory. After everything we've discussed, it almost feels impossible. How can a universe containing so much light still appear so dark? The answer emerges only when all the pieces come together. The universe is finite in age. Light travels at a finite speed. Space expands. Ancient photons become stretched. Much of the radiation shifts beyond visible wavelengths. Dust and gas reshape what we see. Dark matter influences cosmic structure. Dark energy drives expansion, and immense distances separate luminous objects across the cosmos. None of these factors alone completely explain the darkness. Together they do. The dark sky becomes understandable, but something else happens along the way. The darkness transforms from a problem into a clue, and clues are incredibly valuable in science. Imagine trying to solve a mystery. Every piece of evidence matters. A footprint, a fingerprint, a forgotten note, an unexpected absence. Sometimes what isn't present becomes just as important as what is. The night sky belongs to that category. The darkness itself is evidence. Evidence that the universe cannot simply be an infinite eternal sea of stars. Evidence that the cosmos possesses a timeline. Evidence that cosmic history matters. This idea still amazes me. The sky above us contains information, not hidden in secret codes, not hidden in complicated mathematics, visible to anyone willing to look upward and ask a question. Why is it dark? That simple question ultimately helped transform cosmology. Without it, some of the most important discoveries in astronomy might have taken much longer to emerge. Sometimes science advances because observations become more detailed. Sometimes it advances because somebody becomes curious about something everyone else ignored. The darkness of space was one of those ignored things. People spent centuries focusing on the stars. The darkness quietly waited in the background. Then eventually someone realized the darkness had a story to tell, and what a story it turned out to be. Think about everything hidden inside that black sky. The finite age of the universe, the existence of cosmic horizons, the expansion of space, the stretching of light, the afterglow of creation itself, the darkness points toward all of them. Remove any one of those ingredients and the night sky changes. Remove enough of them and darkness disappears entirely. And that's why astronomers eventually stopped viewing darkness as a trivial detail. The darkness isn't incidental. The darkness is diagnostic. It reveals properties of the universe, the same way a doctor's measurement reveals information about a patient, the same way tree rings reveal information about climate history, the same way fossils reveal information about ancient life. Darkness reveals information about cosmic history. And perhaps even more importantly, it reminds us how limited human intuition can be. Consider how this story began. The question sounded simple. Stars are bright. Why isn't the sky bright too? At first glance, the answer seemed obvious. Perhaps there simply aren't enough stars. But that explanation failed. Then other possibilities emerged. Dust, distance, hidden light, expansion. Again and again, the universe proved more complicated than expected. Reality rarely conforms perfectly to common sense. Astronomy teaches that lesson repeatedly. The Earth feels stationary. It isn't. The Sun appears to orbit Earth. It doesn't. The stars seem fixed. They're moving. Space appears empty. It isn't. Darkness looks simple. It isn't. Each layer of understanding reveals another beneath it. The universe rewards curiosity. The darkness of space is one of the finest examples. There is also something profoundly humbling about this story. For much of human history, people naturally assumed that what they could see represented most of reality. It's an understandable assumption. Vision feels powerful, reliable, direct. Then, astronomy began exposing its limitations. Invisible radiation fills the cosmos. Dark matter outweighs visible matter. Dark energy dominates the large-scale behavior of the universe. The cosmic microwave background surrounds us continuously despite remaining invisible to human eyes. Again and again, reality extends beyond immediate perception. The darkness overhead reminds us of that. Every black region of sky represents a boundary between appearance and reality. Not because the darkness is hiding something deliberately, simply because the universe is larger and more complex than our senses evolved to comprehend. Human eyes are extraordinary biological instruments. Yet they were shaped by life on Earth, not by the needs of cosmology. They evolved to detect sunlight reflected from nearby objects. They did not evolve to detect microwave radiation from the early universe. They did not evolve to map dark matter halos. They did not evolve to perceive infrared galaxies billions of light years away. As a result, much of reality remains hidden until science builds new tools. In a sense, astronomy is the story of extending our senses. Every telescope expands perception. Every detector reveals previously invisible phenomena. Every discovery enlarges reality, and often the darkness serves as the invitation. Something appears missing. Astronomers investigate. A new layer of the universe emerges. The process repeats. One reason I find this so fascinating is that darkness often carries negative associations in everyday life. People associate darkness with ignorance, uncertainty, absence. Yet cosmology turns that idea upside down. The darkness of space became one of humanity's greatest teachers. Without it, we might never have realized that the universe has a finite age. Without it, we might have misunderstood the large-scale structure of reality. Without it, cosmology itself might look very different today. The darkness was not an obstacle. The darkness was a guide. It pointed toward deeper truths. That reversal feels uniquely scientific. Science often discovers value in unexpected places. The ordinary becomes extraordinary. The overlooked becomes essential. The background becomes the main story. A dark sky is about as ordinary as observations get. and yet it ultimately revealed the history of the cosmos. There is another lesson hidden here as well. Many of the universe's most important clues are subtle, not dramatic, not spectacular, subtle. The expansion of space does not announce itself to casual observation. The cosmic microwave background is incredibly faint. Dark matter cannot be seen directly. The age of the universe is not written across the sky in giant letters. The clues exist. They simply require patience, careful thinking, curiosity. The darkness of space exemplifies that beautifully. At first glance, it seems to contain nothing. Look more carefully, and it contains everything. History, physics, cosmology, the story of creation itself. It's almost impossible not to admire that. A child looking up at the stars can ask the same question that puzzled generations of astronomers. Why is the sky dark? The wording may differ, the details may differ, but the curiosity remains the same, and remarkably, the question still leads toward profound answers. Some scientific mysteries become inaccessible without advanced training. This one begins with simple observation. The complexity arrives later. The curiosity comes first. Perhaps that's why the story remains so compelling. It reminds us that science doesn't always begin with equations, sometimes it begins with paying attention. Really paying attention. Looking at something familiar and refusing to take it for granted. The darkness of space rewarded exactly that kind of attention, and as our understanding improved, the darkness acquired a new meaning. No longer merely the absence of visible stars, no longer merely the background behind constellations. Instead, it became a record of cosmic history, a visible consequence of invisible processes, a reminder that the universe evolves, a reminder that light has limits, a reminder that we occupy a specific moment in an ongoing story. That last point may be the most remarkable of all. The dark sky is not timeless. It reflects the current state of the universe. Billions of years ago, conditions were different. Billions of years from now, conditions will be different again. The cosmos evolves. The appearance of the sky evolves with it. We happen to live during an era when stars still shine abundantly, galaxies remain visible, and cosmic history can still be reconstructed through observation. Future astronomers, if future astronomers exist, may inhabit a very different universe. Some distant galaxies will eventually become unreachable, expansion will continue, observational horizons will change, the night sky itself will evolve. The darkness we know today belongs to a particular chapter in cosmic history, and that realization connects us back to where we started. The original question seems simple. Why is space so dark when stars are so bright? Now, after exploring the answer, the question feels larger. The darkness exists because the universe has a history, because light takes time to travel, because space expands, because reality is more subtle than appearances suggest. The darkness exists because the cosmos is not static. The darkness exists because the universe is real, not an abstract mathematical object. Not an eternal, unchanging stage, a real evolving universe with a beginning, a history and a future. Every dark patch of sky quietly reflects that fact. Tonight, if you happen to look upward before sleep, the stars may appear much the same as they always have. The constellations will still be there. The darkness will still stretch between them. Nothing visible will have changed, and yet perhaps the view will feel slightly different. Not because the sky changed, because you know something about it now. You know that the darkness is not empty. You know that invisible radiation crosses the cosmos. You know that ancient light from the early universe still surrounds us. You know that countless photons are still travelling through expanding space. You know that much of reality exists beyond immediate perception. Before we finish for tonight, I'd like to return to where we began. Not to the beginning of the universe, not to the first stars, not to the ancient glow left behind by the Big Bang. just to a simple human experience: looking up. For most of our lives, the night sky exists in the background. It's something we occasionally notice, something we admire during a walk, something we glance at through a window before going to sleep. Sometimes we stop and look at the stars, sometimes we don't. Yet the sky has always been there, patiently waiting above every generation. The same darkness that surrounded ancient civilizations surrounds us now. The same stars observed by sailors crossing oceans still shine overhead. The same questions that puzzled people thousands of years ago remain available to anyone willing to ask them. That continuity is easy to overlook. Human lives are brief. History feels long. The universe stretches far beyond both. And throughout all of it, people have continued looking upward, wondering, questioning, trying to understand what they were seeing, or perhaps more accurately, trying to understand what they weren't seeing. Because tonight's story was never really about stars alone. It was about the darkness between them. That darkness seemed so ordinary at first, almost too ordinary to deserve attention. After all, night is supposed to be dark. That's what makes it night. Yet as we've discovered, the darkness above us is anything but simple. The black sky isn't merely empty space. It isn't merely the absence of brightness. It is the visible consequence of countless processes working together across billions of years. The darkness exists because the universe has a finite age. The darkness exists because light requires time to travel. The darkness exists because space expands. The darkness exists because ancient radiation stretches beyond visible wavelengths. The darkness exists because distances between stars and galaxies are almost unimaginably vast. What seemed like nothing turned out to contain an entire scientific story. In some ways, that's one of the most beautiful aspects of astronomy. The universe continually reminds us that appearances can be deceptive. A bright star may actually be dead, its light only now reaching us after a journey of centuries. A dark region of space may conceal thousands of hidden stars behind curtains of dust. An apparently empty patch of sky may contain galaxies too distant and faint for human eyes to detect. The cosmos often reveals itself in layers. Each answer leads to another question. Each discovery uncovers another mystery. And perhaps that's exactly why people never seem to grow tired of looking upward. The sky changes very slowly. The stars appear familiar, yet the meaning behind them continues expanding. A child can look at the night sky and feel wonder. A professional astronomer can look at the same sky and feel wonder. The details differ, the knowledge differs, the wonder remains. There's something profoundly human about that. For thousands of years, our understanding of the universe changed dramatically. The Earth stopped being the center of everything. The stars stopped being tiny lights attached to a celestial sphere. The Milky Way stopped being the entire cosmos. The universe itself became larger and stranger with every generation. Yet despite all those changes, one experience remained surprisingly consistent. Looking into the darkness and asking questions. Tonight we know far more than our ancestors did. We know that galaxies fill the cosmos. We know that space expands. We know that the universe has a measurable age. We know that invisible forms of radiation surround us. We know that dark matter and dark energy influence cosmic evolution. Those discoveries transformed astronomy, yet they never eliminated mystery. If anything, they expanded it. Because every answer revealed additional layers of complexity. The universe became larger, older, more intricate, more surprising. There is a temptation, when discussing astronomy, to imagine that science gradually removes mystery from the world, as though understanding something makes it less remarkable. I've never thought that was true. In fact, the opposite often happens. The more we understand, the more extraordinary reality becomes. Consider the darkness of space. At first glance, it's easy to dismiss. A black background, nothing more. Then you learn that the darkness helped reveal the age of the universe. You learn that ancient light still fills that darkness. You learn that invisible matter shapes galaxies within it. You learn that the darkness itself contains information about cosmic history. Suddenly the black sky becomes richer than before, not poorer. Knowledge doesn't erase wonder, it deepens it. Perhaps that's why astronomy remains so compelling. Every discovery adds perspective, and perspective changes how we see familiar things. A star becomes more interesting when you realize its light began traveling before your grandparents were born. A galaxy becomes more interesting when you realize its photons spent millions of years crossing space. A dark sky becomes more interesting when you realize it contains clues about the origin and evolution of the cosmos itself. Everything gains context. Everything gains depth. There is another aspect of this story that feels worth reflecting on. Throughout our journey, we've repeatedly encountered limits, the finite speed of light, the limits of human vision, the limits imposed by cosmic horizons, the limits created by time itself. At first, limits can seem frustrating. We often imagine that perfect understanding would require unlimited access, unlimited visibility, unlimited information. Yet the universe doesn't work that way. Reality comes with boundaries, and strangely enough, those boundaries are often what make discovery possible. If light travelled infinitely fast, the night sky would tell a different story. If the universe were infinitely old, the darkness might disappear. If everything were immediately visible, many scientific clues would vanish. The very limits that constrain us also reveal information. The darkness exists because reality has structure, because history matters, because time matters. The black sky is not a flaw in the universe. It is evidence that the universe possesses a story, a beginning, an evolution, a future. Without those things, the sky would look very different. Sometimes people ask why astronomy matters. It's a fair question. After all, galaxies billions of light years away don't seem particularly relevant to daily life. The expansion of space doesn't help with household chores. Dark matter doesn't pay bills. The cosmic microwave background won't make your coffee in the morning. Yet astronomy offers something else, perspective, and perspective can be surprisingly valuable. When we learn about the universe, we learn something about scale. We learn how large reality really is. We learn how brief human history is compared to cosmic history. We learn how extraordinary it is that conscious beings exist at all. Not in a mystical sense, simply in a statistical sense. The universe spent billions of years forming stars. Stars forged heavier elements. Planets emerged. Life appeared. Eventually, creatures evolved, capable of asking questions about the darkness above them. That chain of events is remarkable, not because it makes humanity the centre of the universe, quite the opposite. It reminds us that we are participants in a much larger story, a story that began long before us and will continue long after us. Yet for a brief moment we get to observe it, we get to wonder about it, we get to learn from it, and perhaps that's enough. One of my favourite aspects of the night sky is that it remains accessible. You don't need a giant observatory. You don't need advanced mathematics. You don't need specialised equipment. You can simply step outside, look upward, and participate in the same experience that inspired generations of thinkers before you. The stars don't care whether you're an expert. The darkness doesn't care how much astronomy you know. The sky remains available to everyone. That accessibility feels important, especially in a world that often moves very quickly. The universe operates on different timescales. Stars evolve over millions or billions of years. Galaxies drift through space over incomprehensible distances. The expansion of the cosmos unfolds so gradually that human lifetimes barely register against it. Looking at the night sky can be a reminder of that. A reminder that not everything needs to happen immediately. A reminder that reality contains rhythms larger than our daily concerns. Sometimes that perspective feels comforting, at least it does to me. The darkness overhead can seem lonely if viewed one way. Viewed another way, it becomes connective. Every person who has ever looked at the stars has encountered the same fundamental mystery. Ancient astronomers, medieval travellers, modern scientists, children seeing the Milky Way for the first time, all of them shared the same sky, different knowledge, different cultures, different eras, the same darkness, the same curiosity. There is something quietly reassuring about that continuity. Questions survive, wonder survives, curiosity survives, and the universe continues offering new things to discover. Even now, astronomers are building more powerful telescopes, observing more distant galaxies, investigating dark matter, studying dark energy, searching for answers to questions we haven't fully solved. The story isn't finished, far from it. Every generation inherits new mysteries. Every generation contributes new understanding. The darkness still has secrets left to reveal. Perhaps it always will. As we begin winding down for the evening, it's worth remembering how this entire journey started. A simple question. Why is space so dark when stars are so bright? Not a complicated question, not a technical question, a simple observation. Yet from that observation emerged discussions about the age of the universe, the expansion of space, the nature of light, the formation of galaxies, invisible matter, and the earliest observable moments of cosmic history. That's the power of curiosity. One small question can open enormous doors. The universe often rewards people who pay attention, especially to things that seem ordinary. The darkness of space seemed ordinary. Now it feels different, not because the sky changed, because we understand more about what we're seeing, or perhaps more accurately what we're not seeing. The blackness between the stars is no longer empty. It contains history. It contains evidence. It contains clues. It contains light beyond human vision. It contains the faint afterglow of creation itself. And somehow, despite everything we've learned, the sky remains just as beautiful as before, maybe even more so. So if you happen to glance upward sometime soon, perhaps before drifting off to sleep, perhaps tomorrow evening, perhaps weeks from now, the darkness may look familiar. The stars will still shine. The black spaces will still stretch between them. Nothing obvious will appear different. Yet hidden within that familiar view is one of the greatest scientific discoveries humanity has ever made. The realization that darkness is not merely the absence of light. It is a message carried across billions of years, a message about history, distance, time, and the nature of the universe itself. And as the Earth continues its quiet journey around the Sun, while the Sun continues its journey through the Milky Way, while the Milky Way drifts through an expanding cosmos filled with ancient light and unseen mysteries, that message remains overhead every night, waiting patiently in the darkness, just as it always has for anyone curious enough to look up and ask why the sky is dark at all.